ovaj, neću govoriti 1, 2, nego ću govoriti pi, i, korijen iz -1. Poštovane dame i gospodo, uvažene gošće i gosti, kolegice i kolege, dobrodošli na Mašinski fakultet Univerziteta u Sarajevu i dobrodošli na radionicu o membranskim tehnologijama kompanije Higrakon, koja ovu radionicu organizuje u saradnji sa nama, sa Mašinskim fakultetom. Moje ime je Muris Torlak, ja sam profesor na odsjeku za energetiku, procesnu tehniku i okolinsko inženjerstvo i ovdje sam u ime našega dekana, profesora Harsa Lulića, da vas pozdravim, da vam izrazim dobrodošlicu i uspješan rad tokom današnje radionice. Profesor Lulić, dekan našeg fakulteta, je nažalost spriječen zbog drugih obaveza koje se odvijaju paralelno ovome događaju, ali to ne znači da je na neki način preusmjerena podrška. Ovdje imamo priliku da učestvujemo u jednom događaju koji je na neki svoj način i jedinstven, a cilj je prvenstveno povezivanje partnera u industriji sa najnovijim tehnologijama u oblasti membranskih tehnologija prečišćavanja otpadnih voda. Koliko je događaj značajan govori i to da imamo i goste iz inostranstva, učesnike iz inostranstva koji će držati predavanja o aktualnim temama iz kompanija kao što su Hummel, New Logic Research i American Water Chemicals. I drago mi je da imamo priliku čuti takve aktualne informacije i priliku upoznati se sa njihovim radom i njihovim tehnologijama, dostignućima i dobiti nešto od tih saznanja koja ćete eventualno kasnije i vi primijeniti u praksi. Mi kao univerzitet, odnosno obrazovno naučno istraživačka ustanova, imamo također za cilj da budemo u kontaktu sa tim modernim tehnologijama i da doprinesemo razvoju našeg društva i naše zajednice, tako da saradnja i komunikacija s vama će nam također biti jedna prednost i da kažemo možda i odskočna daska za neke druge poslove u ovome pravcu u budućem vremenu. Što se tiče organizacije samoga događaja, imat ćete u toku dana jednu pauzu, pa bih vam preporučio da to iskoristite za međusobnu komunikaciju i networking koliko vam to bude bilo moguće. Naravno da aktivno pratite izlaganja. Izlaganja će biti i na engleskom jeziku, tako da oni kojima je potrebno prevođenje sa engleskog jezika mogu iskoristiti situaciju i tehniku koju imamo ovdje instaliranu. Dakle, kod kolega koji se nalaze u gornjem dijelu prostorije imate na raspolaganju slušalice, tako da ćete moći dobiti simultani prevod. Što se ostaloga tiče, dakle, bit će vrlo zanimljivo, vrlo interesantno, dinamično, tako da, eto, pozivam vas da aktivno pratite i sudjelujete i sa svojim možda idejama, komentarima, pitanjima nakon izlaganja predavača. Na ovome mjestu predajem riječ i gospodinu Arminu Hadžialiću, kojem se u isto vrijeme i zahvaljujem na saradnji, podršci i, da kažemo, usmjeravanju u ovome pravcu. Hvala.
Hvala, profesore. Ako po protokolu ću prvo reći uvodnu riječ, ali prije toga da vam se svima zahvalim. Hvala vam što ste se odazvali. Mnogo lijepih poznatih lica i prijatelja mojih i ako Bog da i novih prijatelja je tu. Poštovane dame i gospodo, uvaženi gosti, kolege i prijatelji. Veliko mi je zadovoljstvo i čast poželjeti vam srdačnu dobrodošlicu na Balkansku radionicu Membranskih tehnologija koja se danas održava na Mašinskom fakultetu u Sarajevu. Posebno nas raduje što imamo priliku ugostiti učesnike iz različitih zemalja, što ovoj radionici daje međunarodni karakter i dodatnu vrijednost. Vaše prisustvo potvrđuje značaj teme kojom se bavimo, ali potrebe za razmjenom znanja, iskustava i savremenih rješenja u oblasti membranskih tehnologija. Predavači na danas eksperti iz vodećih međunarodnih kompanija u oblasti membranskih i naprednih tehnologija obrade vode. Među njima je Arif Karahiloglu, predsjednik kompanije Hummel, zatim Greg Johnson iz kompanije New Logic Research, kao Gabriele Brumer i Daniel Stronč iz kompanije American Water Chemical. Gospodin Greg Johnson će se na današnjoj sjednici pridružiti putem online uključenja. Oni će danas kroz svoja stručna izlaganja predstaviti najnovija dostignuća, praktična iskustva i savremene pristupe u oblasti membranskih tehnologija, procesa te optimizacije sistema za prečišćavanje sa posebnim fokusom na primjenu u realnim industrijskim i komunalnim uslovima. Membranske tehnologije danas imaju ključnu ulogu u procesima prečišćavanja vode, zaštiti okoliša i održivom upravljanju resursima. Upravo zato je ova radionica prilika da zajedno razmotrimo izazove s kojima se suočavamo, ali i da predstavimo inovativne pristupe i tehnologije koje mogu unaprijediti praksu u našim sredinama. Nadamo se da će današnji program biti inspirativan i koristan za sve učesnike, te da će potaknuti kvalitetnu diskusiju, nove ideje i buduću saradnju. Kada govorimo o viziji razvoja regionalnih partnerstava, posebno u kontekstu kompanije Higrakondeo Sarajevo i savremenih membranskih tehnologija, govorimo zapravo o jednoj nužnosti, a ne samo o strateškom izboru. Danas više nije dovoljno razvijati projekte unutar granica jedne države. Izazovi u oblasti upravljanja vodama, zaštite okoliša, energetske efikasnosti su zajednički cijelom regionu. Upravo zato regionalna saradnja postaje ključni alat za razvoj održivih i tehnološki naprednih rješenja. Kompanija Higrakondeo Sarajevo sa više od 15 godina iskustva i preko 500 projekata iz oblasti hidrotehnike i vodoprivrede, tehnologije tretmana voda, zaštite okoliša, energetike, građevinskih i infrastrukturni objekti, već danas pokazuju da je moguće graditi mrežu partnera koja uključuje javne institucije, međunarodne organizacije i privatni sektor. Ta mreža nije samo formalna, ona predstavlja temelj za razmjenu znanja, iskustava i inovacija. Primjer jednog takvog uspjeha je završetak EU za izradu planova zaštite od erozije i projektne dokumentacije za infrastrukturu zaštite od poplava u Bosni i Hercegovini, čiji investitor je bila delegacija Europske unije u Bosni i Hercegovini. Kroz ovaj projekat kompanija Higrakondeo Sarajevo je uspješno koordinirala i sarađivala s javnim institucijama u BiH, međunarodnim organizacijama, Europskom komisijom te privatnim sektorom. Ovakav model partnerstva omogućuje integraciju lokalnog znanja i europskih standarda, čime su razvijena kvalitetna tehnička rješenja za regulaciju vodotoka, smanjenje rizika od poplava i unapređenje upravljanja vodnim resursima. Voda je jedan od najvažnijih prirodnih resursa bez kojeg nema ni života, ni razvoja privrede, ni stabilnih ekosistema. Ipak, paradoks savremenog društva je da upravo taj resurs koji je neophodan za sve svakodnevno sve više zagađujemo. Otpadne vode iz industrije, komunalnih sistema i poljoprivrede značajno opterećuju naše rijeke, jezera i podzemne vode. U mnogim slučajevima prirodni kapaciteti samoprečišćavanja više nisu dovoljni, što dovodi do narušavanja kvaliteta vode koje direktno utiču na zdravlje ljudi i na okoliš. Zemlje našeg regiona suočavaju se sa vrlo sličnim izazovima. Od zastarjelih sistema za prečišćavanje otpadnih voda preko ograničenih kapaciteta postojećih postrojenja, pa sve do potrebe usklađivanja sa savremenim evropskim direktivama i standardima. Upravo ta zajednička problematika otvara prostor za jaču regionalnu povezanost i razmjenu znanja, iskustava i tehnologija. U tom kontekstu membranske tehnologije predstavljaju jedan od najvažnijih pravaca u savremenom razvoju. One omogućavaju visok kvalitet tretmana otpadnih voda, stabilan rad sistema i značajno smanjenje potrebnog prostora u odnosu na konvencionalna rješenja. Potrebno je važno istaći njihovu fleksibilnost i mogućnost primjene u različitim skalama, od manjih lokalnih sistema do velikih industrijskih i komunalnih postrojenja. Međutim, nijedna tehnologija sama po sebi nije dovoljna bez šire saradnje i razmjene znanja. Zato je razvoj regionalnog partnerstva ključan, jer voda ne poznaje granice, a ni zagađenje se ne zaustavlja na administrativnim linijama. Rijeke i vodni sistem povezuju cijeli region i upravo zato je neophodan zajednički pristup njegovoj zaštiti. Razvoj regionalnih partnerstva u ovoj oblasti treba da se ogleda kroz zajedničke projekte, pilot postrojenja i demonstracione objekte gdje bi se nove tehnologije testirale i optimizirale u realnim uslovima. Takav pristup omogućava ne samo tehnički napredak, nego i jačanje povjerenja među institucijama, privatnog sektora i akademske zajednice u različitim državama. Poseban značaj ima i usklađivanje sa evropskim standardima i praksama, jer ono predstavlja ključan okvir za dugoročno održivo upravljanje vodnim resursima i daje integraciju regiona dalju integraciju regiona u evropske tokove. U kontekstu membranskih tehnologija za prečišćavanje voda, regionalna partnerstva imaju nekoliko ključnih pravaca razvoja. Prvo, transfer znanja i tehnologije. Membranske tehnologije su dinamično područje koje se brzo razvija. Saradnja sa univerzitetima, istraživačkim centrima i međunarodnim ekspertima omogućava da najnovija rješenja brže dođu do praktične primjene. Upravo ova radionica je primjer takvog povezivanja nauke i privrede. Drugo, zajednički projekti i investicije. Region Balkana dinamične izazove od tretmana komunalnih i industrijskih otpadnih voda do potencijom vodnih infrastruktura kroz partnerstva moguće većeg obima, koji su finansijski i tehnički te atraktivniji za međunarodne fondove i institucije. Treće, standardizacija i podizanje kvaliteta. Kroz saradnju sa partnerima iz regiona i Evropske unije moguće je uskladiti tehničke standarde i implementirati najbolje prakse. To direktno doprinosi projekata i dugoročnoj održivosti sistema za prečišćavanje vode. Četvrto, razvoj lokalnih kapaciteta. Regionalna partnerstva ne znači samo razmjenu, ona znači i stručnjaka. Kroz zajedničke projekte razvijamo kadrove koji će nositi razvoj ove oblasti. Vizija Higrakona Sarajevo jeste jedan od vodećih aktera u regionu inženjeringa uz visok nivo kvaliteta usluga. Ta vizija se ne može ostvariti izolovano, stvari upravo kroz partnerstva. Higrakon je uspostavio i predstavništva renomiranih međunarodnih kompanija Tangent, New Logic Research, Pollution Engineering i American Water Chemical, čime je dodatno ojačao svoju poziciju u sektoru membranskih i vodoprivrednih tehnologija. Zato današnji skup nije samo stručna radionica, ona je platforma za povezivanje, mjesto gdje se susreću ideje, iskustva i ljudi koji dijele isti cilj, razvoj održivih, efikasnih i inovativnih rješenja u oblasti voda. Na kraju želim naglasiti, budućnost membranskih tehnologija u našem regionu zavisi upravo od naše spremnosti na saradnju. A ta saradnja počinje ovdje kroz dijalog, razmjenu znanja i stvaranje novih partnerstava. Naš krajnji cilj nije samo tehnološki napredak, već i dugoročna zaštita vodnih resursa i održivi razvoj cijelog regiona. Želimo da se kroz saradnju razvije snažna regionalna mreža znanja i odgovornosti prema vodi. Mreža koja će omogućiti da vodu ne posmatramo kao problem koji rješavamo, nego kao resurs koji čuvamo za buduće generacije. Na kraju želim se zahvaliti svima koji su doprinijeli organizaciji ove radionice, kao i vama koji ste izdvojili svoje vrijeme da budete ovdje s nama. Želim vam uspješan i produktivan rad te ugodan boravak u Sarajevu. Hvala vam na pažnji. Sad bi pozvao kolegu Daniela Strondža iz American Water Chemicala. Gospodin Strondž ima dugogodišnje međunarodno iskustvo u oblasti tretmana voda i upravljanja hemijskim procesima u membranskim sistemima. Danas će govoriti na temu transformacija tržišta tretmana voda, globalni trendovi i operativna efikasnost. Njegovo izlaganje će obuhvatiti savremene promjene u industriji, ključne globalne trendove, kao i praktične pristupe unapređenju operativne efikasnosti u sisteme za prečišćavanje voda. Daniel, please.
Dobro jutro. Kako ste? Sam često danas ovdje i što mogu da pričam pred svima vama. Hvala puno, Higrakon. Ja sam Italijan, pričam malo, razumijem malo i želio bi da šestnja Bosni i Hercegovini na plazmanu na svjetsko prvenstvo. Ajmo Bosni i Hercegovini. Sad engleski. Može? Good day, everyone. My name is Daniele Strongone, and I'm the general manager for American Water Chemicals. and the president of the Water Positive think tank. This morning, I'm gonna touch two different sides of my presentation. First, I'll talk about AWC, what do we do, and how we are present in the world and here in the Balkan region, thanks to Igracon, our local partner, and what can we provide together with Igracon for the Balkan market. And I'm gonna then move to a presentation about Water Positive, the initiative, how Water Positive concept differs from the carbon negative concept, what's the similarity, and what's going on right now. So how the water market is transforming and which are the opportunities for all of you in this room and who is connected online, of course. Okay, let me see. Perfect. So we are based in the US and in Spain since 1993. Gabi and I, we are coming from Spain, which is our international division, and our HQ is in Florida, United States. That's a quick company map where we came from. We come from an engineering company, so something similar to most of you. But then we transformed ourselves during the 90s, more or less, starting selling chemicals also together with engineering, to then just grow more on the chemical side. So we decided to sell the engineering side, the OEM side of the business in the early 2000s, and just stay ourselves as a chemical company. Chemical company serving all the water market where membranes are present. So desalination, water reuse, industrial process, zero liquid discharge nowadays. Along the years, we develop internally several process, several systems, several products, several softwares. Gabi is going to present later on Proton, and to see how we can help our customer maximizing the recovery and understanding how their process can work in the best way. We found our international division back in the 2020, 2022. In 2023, we start working openly international from Barcelona as well. So we have Florida and Spain as main hubs. And what do? We manufacture antiscalant, cleaning chemicals, biocide. That's the biggest focus. And our portfolio also includes some service, so we can offer support with water analysis evaluation. So after you guys have collected locally the water analysis, we can help evaluating those membrane autopsies, cleaning study, and all our softwares that I'm not going to spend much words on this because Gabi will go through that. We are certified with all this, comply with all this certification. And quickly, I'm going to show you our capabilities. Our HQ in Florida has in-house laboratories where we can offer access to all our partners. So for you guys getting in touch with Igracon, you will be able to use all these services. And these are a little bit the instrumentation we have. Just for you to understand, we also partner with some universities, like the universities in Florida, do some study in our laboratories. Spectroscopy, chromatography, spectrometry, all this is part of our facility where we develop all our projects, all our products in-house. This, for example, are some pictures coming out of an autopsy report. So if some of you is running a system and you start having problem, biofouling problem, scaling problem, where you don't really know what's actually in there, and it's difficult to understand from the water analysis, you can reach out to Igracon, and together with us, we can evaluate which is your problem on the membrane using our autopsies. That's a little bit our facility. I'm just gonna quickly through some image to see what we do. That's our HQ. That's what we have to do cleaning study, web pilot to simulate what's happening on the plant. And this is our distributors map. So where we are all over the world. And as you guys can see, all the Balkan region, can I point? No, the point doesn't work. So you guys can see all the Balkan region is marked with our partner Igracon. They can help you solving problems in all the countries that they can manage, the Bosnia-Herzegovina, Serbia, Montenegro, with all you guys are present, and it's like having AWC on country. So working with Igracon means working with AWC directly. Quick point on how big we are. We are manufacturing right now in the United States and in Europe, in Belgium exactly. We are expanding. We're going to start manufacturing in another facility inside the United States, in Australia, and probably in the Middle East. Hopefully, you know, if the political situation calms down a little bit, we are able to catch up on that. But we have inventory all over the place, so you can reach out to Igracon for any need in terms of product availability. They will be able to help you guys. So quickly, product portfolio, again, anti-scalant, cleaners, and biocides. That's what you need to remember. That's what solves your problem. You have biofouling problem, you have scaling problem. That's where our intervention. So anything that is reverse osmosis membrane related, we are able to solve the issue and provide you with the right solution. We can help reducing the operational costs. That's the major goal from our side. So our goal is not selling the chemical, it's selling the solution. And when I say our, I'm talking about AWC together with Igracon. We work together to solve your problem, to provide you with the right solution and lowering always your operational cost. So we can maximize the recovery. You know, nowadays we're talking a lot about zero liquid discharge, or go as high with the recovery as possible in order to take less water from the environment or to maximize the water you currently have in your facility. You can extend the time between the cleaning of the membrane. That's a very important factor. Whenever you have dirty membrane, you have to clean often. Cleaning often means spending money on cleaning, lowering time, labor cost. So all these factors together, AWC and Igracon, we can provide you the best solution for your specific problem, a target solution. And the main goal is always reducing the operational cost. That's a quick guideline on the anti-scalant selection. So what do you have? Which is your problem in your water? Sulfate, silica, phosphate, carbonate. We have the right anti-scalant to solve that specific problem. And that's exactly the same that happened with cleaning chemicals. So according to the problem you have, we have the right cleaners to supply to avoid your problem and solve the problem. Quickly, why then AWC? Why we decide to partner with Igracon? Why Igracon decide to partner with AWC? To offer the best solution, because we have exclusive membrane focus. We only work on membrane, reverse osmosis, nanofiltration. We're really focused on that. Agility and responsiveness. We are not a huge corporation with 1,000 people. We are a company which is really focused. Same as Igracon. So we are more a customized company. We are closer to our customer. Here in the Balkan, we rely on Igracon as our local partner. So having them is like having AWC here. And AWC can offer all the time technical support and backup support for any of those applications. So a trusted partner, not a competitor, not just another company. Hvala puno. No, put it back, put it back. Can you just open back? That was just the first part. Can you put back? Yeah, that was just the first part. Yeah. Perfect. Yes. Okay, we can now move on the second part of translation. Oh, of course. Yeah, sure. Može? Okay. We're moving into the second part of my presentation, where I'm going to give the modern vision of how the water market is transforming. So we're going to change a little bit the vision from water efficiency to water stewardship. And I'm going to explain what all this means. So the idea, can't see that. The idea is, perfect, thank you. I want to give you an overview because we always here talk about, like, you know, the last few years, you're talking about sustainability. When we talk about sustainability, until a few years ago, the only thought was waste, was carbon, footprint. We didn't really listen a lot about water, right? Water was not in the focus, in the center. So when in March 2023, I visited the UN Water Congress in New York. So I was there attending the Congress, was a presentation, and me, together with another group, small group of people, we were the only people talking about water. Like UN Water Conference, minimal focus on water. Well, that's strange, no? So if you think back, the previous water conference from the United Nations was in 1974, almost 50 years before. It was in Argentina, Mar del Plata. So for 50 years, the world, even the United Nations, didn't really put a lot of focus on water. So talk about sustainability, talk about gas emission, solid waste, because water was always given for granted. And if we don't take action by 2050, if we maintain the situation as it is, almost 4 billion people will be in critical conditions without water. Access, I would say. So it's interesting to understand. We always look at the green, right? Sustainability is green, but there is no green without blue. Water needs to be the focus. So the new structure of the water markets needs to have water in the center. Look at this. This is very interesting. When we see the Earth from above, from the satellite, it looks blue, right? That's a lot of blue. So when we put together all the water available on the Earth's surface, 1,384 kilometers wide will be a sphere with all the water on Earth. Look how small. It's the biggest small. It's the biggest sphere. Still very small compared to the Earth. But then look at the second one. This is if we take all the fresh water that is available. So the lakes, the groundwater, the river, that makes the second sphere. 273 kilometers diameter. But then it gets crazy now. Look at the dot. See this? Wow. Only 56 kilometers of diameter is the real fresh water that we have access to. Because a lot of the fresh water that I mentioned above is not, we don't have direct access. So that's all. That's so small. So between the first UN Water Congress in 1974 and UN Water Conference 2023, where I presented in New York, in 50 years, the global population has doubled. Before, 4 billion people. Now, 8 billion people. But the water is still the same. It's still the small sphere that we have available. So we need to think differently. We need to give focus on this. We need to preserve this. So that's why the SDGs have been written down. You know, when they teach us the water consumption of every person, they say 250, in Europe, 250, 300. That's what we have as an average. Some countries, they have as low as 100. Some countries, maybe a bit more, maybe 400 liters per person. That's not true. That's not reality. That's the water you use every day to shower and drink. Maybe a little bit cooking. That's it. The real consumption that each one of us has every day is between 3,000 and 5,000 liters per day. Why? To create this suit, they need water, right? So I'm actually using water. This morning, I had breakfast. It's not just about cooking. It's about how much water you need for the beef, then to make the meat, for the chicken to give the egg, milk. Consider now, I'm talking on this, that is electricity. To electricity, you need water to cool down the system, right? Internet, data center use a lot of water. So think that everything we do, everything we have around us, it has an impact on water. So each one of us is consuming more or less 5,000 liters of water, not 200. So what does it mean? That really what is impacting is the industry. So SDG 6 is the one that talks about the water consumption, but that's actually not the big one. It's only 10%. The big boy is 90%, is the industry. So SDG 12 is what is really impacting. So there are all these SDGs, there are 17, but all of them, they are connected to water. Some less, some more. So we really want to focus on the industry, and that's why we are here. We are all from industrial company, the industrial markets, we, Igracon, you, and even the university. If we think about university, is preparing people, future engineers, to work for the industry. So each one of us can be responsible on the impact on this water. And that's where the Water Positive initiative started. This is just to show you that most important part is the last sentence. We did water. When we hear like, oh, we're finishing water. No, water is still the same. It's still the three spheres I showed you before. We have broke the system now. 100 years ago, the water cycle was good enough to give us back fresh water after our use. But when the Industrial Revolution happened, we start using way more water than what we need. And that's how a group of us, after the UN Water Conference in New York, founded the Water Positive think tank and started putting together a new concept, a new principle, which is the water positive concept that can define as the concept where an entity, like a company, like all of us, a community, individual as well, a university, a government, a country, goes beyond simply conserving water and actively contributes to a sustainable management and restoration of water resource. That simply means like leave a positive impact on the water resources. So give back to the environment more water than the one we take from the environment. That reminds you of the carbon world, right? Where it's the other way around. You want to act to take back from the environment what you have taken, like, compensate with the emission. Here it's water, so it's liquid, it's not a gas. So we calculate this on 3 dimensions. Quantity, I take 100, I have to give back at least at 101, a little bit more than what I've taken to become positive, no? Quality, of course, I have to provide better quality, I have to give back better quality, and access. So if we're talking about this in the area of Sarajevo, we need to be focused on the area of Sarajevo. And that's a difference between the CO2. I will mention afterwards. So the main part is what we need to focus on. In order to make water positive our projects, we need to have intentionality. So we have to state and define that this is going to happen only when we intervene. That's just because of our intervention, this is going to happen. Additionality, so we're bringing this volume more. So if it was not for us intervening in that project, you could not get to that point. And permanence, that we secure that is going to happen for 10 years or for 15 years. I think you know a couple of these companies, no? They are small companies from the region. No, they are big corporations. So these companies, back in 2015, they gathered together and they create what is called the CO Water Mandate, with the goal of becoming water positive between 2030 Oh, okay. Can you just minimize that? Voila. Okay. Oh. Perfecto. Okay, so how does the carbon offsetting work? So you produce an emissions as a company, as a corporation, as a factory. There is an emission that is produced. So business and organization purchase offset units. The classic thing, planting the trees somewhere, you plant the tree collects a specific amount of CO2 from the air. Imagine you have 10 trees, they collect 10 molecule. You have an emission of 10 molecule, 10, you are neutral, right? So, and that's kind of straightforward thing. People have been planting trees all over the place. I use this one because it's the most common way of setting with trees. But it's in the air, it's gas. So if your emission is in Sarajevo, you can plant your trees in Mostar, or you can plant your trees in Italy. It's gas, goes in the air, so it's okay. It's balanced. Then these offset units cancel your emission, so it became neutral. So why? Why it's so easy? Because carbon is a well-mixed atmospheric gas, so allowing global equivalence. You can do it anywhere and you will be easy. So it's very easy because it's a linear allocation. So anywhere I can plant the tree, the molecule of CO2 is going to be exactly the same. And price-based decision, it's easy because you say, how much is the ton of CO2? It's going to be the same all over the world because you are removing the same ton. With water, it's a little bit more difficult. And look, this is a map of time of how was the evolution of the water benefits. So carbon credits in water, you call water benefit. And you can see here how many new legislation the European Union is issuing in order to incentivize this, in order to make this happening more and more. So for now, the carbon market, it's global, it's set, it's there, same all over the world. For water market, so water benefits market, kind of like water credit, but we call it water benefits, it's still very local. The UN is offering people to start doing it, inviting corporations to start doing it, but it's not an obligation yet. The European Union is start obligating the big players. Big means like over 400 million revenue, over 1,000 employees. So for now, a company like probably all of you guys here is not obliged. A company like AWC is not obliged. Igrafon is not. But we need to start acting first to have a positive impact on the world, on sustainable impact on the environment. And second, because it's a monetizing opportunity. Here there is a financial opportunity for all of us, because if you remember these guys here, they are obliged. So they are looking to buy these water benefits. So companies like us can prepare the ground and can offer this benefit for them. I'm going to show you how. And a company like AWC and Igracon here in the Balkans can help all of you guys generating these water benefits and sell them to them. That's going to create a marketplace. So I mentioned in carbon world, you say carbon credits, water, we call it volumetric water benefits. And the volumetric water benefit accounting is a methodology developed by the Water Resource Institute to quantify the volume of water benefits, like how much water benefits generate by project and actions relative to a defined baseline. So we have a base in hydrological region, and we will focus on that. That's the difference with carbon. Remember before I said, carbon, you can plant your tree anywhere and offset your emission. With water, no. If you are impacting in this water basin, you cannot compensate in Spain because you are damaging this water basin. So you need to act on this water basin. So you define the baseline, so where we have the intervention, identify the action, so maybe improve the efficiency of the system, or reuse some of this water, or recharge, they're having an impact. Then you quantify the benefits, so how much, and that's where the trading part starts coming in, and express this as a water benefit. So I'll show you in a bit how can be done. And this is one of the, like this is a huge list actually of how can we create these water benefits. We can do wetland restoration, aquifer recharge, water reuse and recycling. But what I really want to focus in today, because this is a membrane workshop, we're all here working with membranes, especially reverse osmosis membranes, it's water savings and treatment efficiency. So how can we work better on an existing system? You have a narrow reverse osmosis system plant. If we make it run better, make it more efficient, we can monetize on that. We can generate this volumetric water benefit and enable the trading. Okay, this was a different format. Now on these colors, you cannot see anything, but it's basically to say that in the project, there are three main people. The corporations I mentioned before, Amazon, Google, Microsoft, Coca-Cola, the beneficiary, so the community that lives in that specific area, that's in the image, there is a person, and the developer. You all can be developers. AWC is a company with a co-developer, we say. We help companies that operate the system, like the owner of the system. They will be the developer because they own the system. We help them, and Igracon together with us will do it in the Balkan, improving the system. So the developer, means each of you owning or running a plant, can generate and create these water benefits. This presentation will be available for you guys. This is better if you guys read and absorb. It's a difference between water management and water stewardship. I think it's a nice summary I create for you, so you can understand in every step what is different. Because up to 10 years ago, there was no difference. When people were talking about water stewardship, oh, same as water management. No, it's different concept. Nowadays, we don't talk anymore. We don't want to talk about water management. We want to talk about water stewardship because it includes the SDG, the sustainability, and the water positive ideology. So what I was saying before, in this change of the water market, how a company like AWC plays as the water benefit developer together with you guys, with the owner of the plant, because we can help increasing the recovery. We can help get to maybe to a zero liquid discharge or as close as possible to that. And with our local support here, thanks to Igracon, is how we can technically support companies like you to achieve that goal and then connect with this corporation that they want to buy the volumetric water benefit. So again, it's a little bit of a summary that for you guys to read afterwards. You will have access to this presentation, and it's really explaining, like, again, the water stewardship meaning and how you can take part of it. This is a clean and easy case study that makes you, like, better understanding on the volumetric water benefits, how this is done, and it's with a data center. So all the companies that I listed before, the corporations, so the first starts talking about water positive were the beverage company. So we need to be honest here. The first one who mentioned this were Coca-Cola and Pepsi. But right now, the biggest one really focusing on this are the tech companies. Meta, Google, Microsoft, and Amazon. So this is an example of a case study of a data center where the volumetric water benefit help compensate for the water loss through industrial activity by creating and protecting an equivalent amount of fresh water. Company X runs a center, imagine, takes all the time 100 liters of water. It's a data center, so it has loss in evaporation. So water efficiency alone is not enough. Time water due to evaporation. So you need to compensate to this loss producing new fresh water. So the company running the data center compensate this loss of, let's say, 10. Okay, they take 100, they always lose 10 because of evaporation. So at the end, they remain with 90. They cannot give back to the environment 90. So they're going to be water negative. So in order to be neutral, at least you need to give back this 10 extra more. But if you give 12 more, 11 more, you'll be positive. So what they do, they compensate buying, it's a virtual water, it's not like physically the water. So allocating this credit, as you would call it in the carbon market, here we call it benefits, contracting this to a company who is producing fresh water. So there is a company, can be one of you guys here, that thanks to the help of the support of Y on AWC can increase the recovery, generate a little bit more, and that more that has been generated can be purchased by a tech company to compensate this loss. So they buy 15, so now they are water positive. That's what happened in this specific case. And you will be available to read through these things. It's very interesting. And how this happened, like physical, let's explain. So there are different processes. This is the first one, whoever started was in agriculture. That's the second one who started and was in non-revenue water. So check the water you lose along the process. But that's where the interesting part comes for all of us. Is a volumetric water benefit compensation through water savings. This can only happen with reverse osmosis membrane systems. So what we're here for. How a company like AWC with our product line can help someone to create this water savings. And when I talk about AWC, here locally means Igracon, because they are our arm in country. So with our knowledge, for all of you, we can generate these water savings. You, the owner of the reverse osmosis system, can generate. And I'll tell you how. There is a corporation there, Target Water Compensation, okay? These are the company who is consuming a specific amount of water, 1 cubic meter. So in sustainability market, 1 cubic meter of water is equivalent on 1 volumetric water benefit. Same as you were saying, like, 1 carbon credit for the ton of carbon. So they need to compensate for that. So what they want is to buy a virtual amount of the same volume. At your plant, you are currently recovering 85%, okay? Your reverse osmosis right now is recovering 85%. So you take out from the environment 150 liters of water, and then you produce fresh water for 100 liters, right? That's 75%, let's put it this way. You take 150, you produce 100. But if we can help you with our anti-scalant and our support to increase from 75 to 85, so you take 150, but then you produce 120, or even better, if you want to produce only with that 100, instead of taking from the environment 150, you can take 120 if we have increased the recovery, correct? So this difference, what I was taking before, 150, what I'm taking now, 120, 30, this is the water savings. This is converted in volumetric water benefit, and this is what you can trade to the corporation that want to buy that difference. And I'll show you now, like, what are we talking about? Like, who is going to really buy that? But I think that was clear example. If you have any question for that, you can send me an email, you can ask me anything. But just remember, I increase the recovery of my reverse osmosis system. I use less water from the environment. I'm creating savings. If you think about that, if you get as close as possible to zero liquid discharge, to produce 100, you're going to take as close as 100. It's never going to be probably 100, but 105. You were taking 150 before. Now you take 105. This 45 is a very big difference. And that's what you can trade. So a company like you can monetize, can make money thanks to intervention of a company like AWC. The same happens when it's on water reuse. So increasing the recovery, instead of like, you have a wastewater, you transform in clean water, 75% of it, and you throw away 25. If you can increase how much water I transform into good drinking water, from 75, I make 95. I'm only throwing back to the environment a small amount of dirty water in the concentrate. That means that I've increased of 20%. I can trade that 20% as volumetric water benefit. And again, this is like just going beyond the efficiency. It's not being, oh, that's the best I can do. I'm running the plant very efficiency. I clean. No, here, if you can make a little investment and go beyond, that's going to be paid back a lot of money. So how can this happen? How can we, like, if we make these savings, how can then we trade this? Because there isn't an official marketplace. It's still like a gray area. There is this company that's called Aqua Positive, that they create a platform. It's called a marketplace. We are partnered with them. So whenever we have a potential project, they put it on their platform. It's like booking. You want to look for a hotel, you go on booking, you see a lot of hotels. Or there is, in any country, there is like Idealista, or there are places where you can check for, I want to rent a house for living. You have a huge list, and you select which one is the more appropriate for you. You select by region. So you can go on this platform and see, for example, South America. These are examples of projects that are in Chile, for the flag. Our office is in Spain. So I say, let's see Spain. So we feed this database, this platform from Aquapositive, with all our projects. There is also other companies similar to AWC working in water savings that feed this platform. Now, the corporations like Microsoft, Coca-Cola, Danone, Nestlé, what they want to do? They want to become water positive. So they want to buy these credits, benefits we say in water, in order to compensate all the water they consume and become water positive. That's benefit them for the reporting in the CO water mandate I showed before, reporting to the European Union. And one day this will be global. So the UN is working on a global marketplace. So imagine they have a data center in Spain. Actually, this is reality, I'm not imagining, it's real data. So they have a data center in Spain. They want to look for where can I compensate. As in the specific, you see here AWC. We have a project in Madrid when we do exactly that, help increasing the recovery of the plant from 75 to 85. The plant operator, someone like you guys, it's creating water savings and it's putting them there and it's trading 0.45 euro per cubic meter. What does it mean? Thanks to us, they are increasing. I don't remember the exact volume. The plant is not that small, so it's a decent volume. But imagine, let's do easy numbers. Like this, we can do easy maths. Imagine is 100,000 cubic meter, the savings that they generate. 0.45 cents per cubic meter means that we're talking about 45,000 euro that the corporation is going to pay the operator. Any of you can be the operator. So this operator in Spain will get 45,000 euro from Microsoft, from Amazon, from who is going to buy this. So Aqua Positive creates the platform. Companies like AWC feed the platform. And we can feed the platform with projects in Bosnia and Herzegovina, in Serbia, in all the Balkans. That needs to come from you. So if in this project, you are currently working at 75%, you contact Nihad. Igracon will help you with AWC product to increase the recovery and bring it to 80%. You don't need to be extreme. You can also increase by 1%. The more you increase, the more you make money. But if you increase to 5%, okay, simple, it's very easy with our chemicals. That difference, we can report on this platform. And if a company like Coca-Cola needs to compensate in the Balkan, they will see your name there, they will see the project there, and they will say, okay, I need to buy this. They're going to fund you for that water. You physically don't touch anything because they're not going to buy the liquid water. They are buying the soul of the water. They are buying the volumetric difference. So it's the virtual water. And you see, this is all over the world. Now you can tell me, oh, that's a very good story, but who knows when this is really going to happen? No, we're already working on that. And I'm going to give you a couple of interesting names for you to see what's going on. Let's start with Microsoft. Microsoft had the scope of like global water replenishment project. So they really focus on replenishment. So bring water down back. So which was their goal? To achieve water positivity by 2030. So return more water to the environment than the one taken to use for their operation. What are the guys doing? Actually, they've already invested 45 million in this project. And this data is from 2023, 2024. So I think last year, sum up, that number will be close to 100 million. Brazil, Chile, India, Indonesia, Mexico. There is no business for them in the Balkans yet. They have factories. Why? There is no business there because they don't have project they can buy. Nobody has already created this volumetric water benefit because there is no obligation. But the European Union, the UN, the corporations are inviting companies like us to cooperate, create that because they need to buy. Coca-Cola. In 2023, they replenish 148% of the water they use for the beverage. Means that every 100 liter of Coca-Cola that they made, yeah, it's Coca-Cola. 100 liters of Coca-Cola that they made, they gave back 148 liters to the environment, or the better quality, and it's coming from a company like us. Where did this happen? It's via the Coca-Cola Foundation, so it's like all over the world, wherever they are present. But here, for example, you see Amazon, US, India, UK, Spain, Brazil, South Africa, Australia, Canada. These are all projects that are happening. And I'm going to tell you something really nice. Actually, it's written there, but it's even better when I say that. 10 plus million in water stewardship project until 2024. Then the market starts pushing, especially in Spain. We do a lot of this work in Spain. And I hope that next year I will be here again. And in the Balkans, there will be like exactly the same kind of work. In 2024, in 2025, sorry, only in one project, they invested 17 million in Zaragoza, Spain. Only one. So I can go like a lot with, there is PepsiCo and all these countries, there is Google, there is Meta, there is Nestlé. So key takeaways, that's going to be for you to read and save. It's the main difference between the carbon and the water market that I've been explaining until now, and why we need to create a proper market for all of us to play and maximize and monetize. I want to close up with a sentence that a good friend of mine taught me a few years ago. The best time to become water positive was 20 years ago when the carbon started. The second best time is now. Ciccia mića, gotova priča. Hvala puno, Sarajevo.
Zahvaljujem se kolegi Danielu na njegovom izuzetno korisnom i inspirativnom izlaganju, kao i na podijeljenim iskustvima i uvidimo savremene trendove u industriji tretmana voda. Sada bih sa zadovoljstvom najavio sljedećeg predavača, gospođicu Gabriele Brumer iz kompanije American Water Chemical, koja će govoriti o proton alatu za modeliranje, simulaciju performanski membranske tehnologije.
Okay. Hi, everyone. How are you doing? Unfortunately, my Bosnian is not as good as Danny's, so I'm just going to stick to English. But today I'm going to be presenting a little bit about the fundamentals of reverse osmosis nanofiltration, how it works, what these systems look like, kind of the science behind them, so that hopefully by the end of this, we can all be a little bit more of membrane experts. So let's get into the fundamentals of reverse osmosis and nanofiltration, which are these membrane technologies that we've been talking about today. So depending on the source water that we're working with, right, whether it's wastewater or surface water or municipal water, our water can contain many different types of constituents or items, right? So this can be something like suspended solids, like silts or clays. It can be also organic constituents that are soluble or insoluble. It can be dissolved gases, like dissolved oxygen. We can also have biological components in our water, so algae or different type of bacteria. And most importantly, we will definitely have dissolved solids. So this is going to be something like sodium or chloride, calcium, that's literally dissolved in our water that we can't see with our naked eye. And so when we talk about reverse osmosis and nanofiltration, what we're really aiming to remove is this portion right here, these dissolved substances from our water, so that we can produce pure water that's very low in these dissolved solids. And so in order to understand what reverse osmosis is, I kind of want to explain what actual osmosis is first. So let's imagine we have a container here with a semi-permeable membrane in the middle. And we have water that's on the two sides of this membrane, one with low TDS or dissolved solids. So again, calcium, sodium, chloride, for example. And on the other side, we have a more concentrated water, right? So this has high TDS. Naturally, the water is going to want to equilibrate the two sides of this container to make sure that the concentration is equal. So we have these little Mickey Mouse looking images, which is our water, and the green, which is our dissolved solids. And by natural processes, the water will move from one side to the other in order to make this concentration equal, right? So now we have the same amount of water as we have solids. This is called osmosis. So this semi-permeable membrane is going to make it so that no dissolved solids can pass through. It really just is the water that's passing. Now, let's say we start to apply a pressure. We're going to start talking now about reverse osmosis. So as we apply a pressure to the higher TDS side, the more concentrated side, we can actually force the water to go to the side that has lower TDS. So like this, we're now working against nature basically, and we're producing a much more pure and clean water with pressure and this semi-permeable membrane. And so this is what we call our permeate from our system, and this is what we're targeting to produce with these reverse osmosis systems. And so you might be familiar with this. This is a membrane element. This is what our reverse osmosis systems are made of. And inside, we have this really interesting kind of configuration. So that same semi-permeable membrane that I was talking about will be wrapped around, kind of stacked almost like a book, and then wrapped around itself and fit inside of these elements. And so this is the way that we're going to start to produce water, which I'll show you in a second. So the center tube right there is where we're going to collect all the clean water that I was talking about after we apply a high pressure. And here I have an image from one of our autopsies that we've done in our laboratory where you can see how this looks in real life. And so this membrane is really interesting the way it's made. It's almost like a plastic. We have 3 different layers, and the part that's doing this process of separation of solids is the very, very top thin layer, that orange layer right there that you see. And so this plastic is very delicate, and we have to keep this in mind when we're running these systems because we don't want to damage our membranes, and we want to make sure that we're continuing to produce our clean water. And so the way that reverse osmosis works about it in a grander scale is that we're going to flow water across these elements. And as we're applying a pressure, we're going to start filtering out all of the clean water and leave behind all of the salts that we want to remove. So we're leaving behind all of the calcium, sodium, chloride that we're trying to remove from the permeate. Now, we not only have these active membrane sheets in our reverse osmosis elements, we also have these feed spacers that help us to separate each one of the stacks in order to have some space to actually flow the water through. So this becomes important, which I'll explain in a bit. But each single membrane will have kind of a different way of designing these feed spacers, which will help increase flow and promote water production down the line. So this is just something to keep in mind as we continue our conversation. Now, we don't have these elements that I showed just exposed to the air in our systems. We'll have them put inside of these pressure vessels, which are rated to handle very high pressures, and they'll help to contain the elements in series. And how it looks inside, because it can be a little bit difficult to see through, is that we'll have multiple of these elements or membranes put in order, and we'll be able to flow water through the bigger, pressure vessel. And from there, we'll be able to concentrate our water more and more and continue producing more clean water. So here you can see as we're going and flowing our water through the system, we're increasing our concentration, so our total dissolved solids or our conductivity, and we are producing more clean water. And so these pressure vessels can basically be organized into stages or passes in order to produce more water or to produce cleaner water. So a stage is a set of our pressure vessels. We can put stages one after another in order to continue producing more clean water, like I mentioned. So here you can see kind of an example in the real world. We'll continue sending the concentrated water to the next stage and producing more clean water from there. Or we can actually take the clean water from one system and send it to another set of reverse osmosis elements, and we can produce even cleaner water, right? So we're sending the clean water, like I mentioned, trying to put pressure to remove more salts, and from there, we're producing that cleaner water. So it looks very similar, but you can see how that piping might be a little bit different in order to achieve this. And so now I want to just touch upon some common operational terms that we hear a lot when we work with these reverse osmosis systems. So these are things like recovery, concentration factor, flux, permeability, cross-flow velocity, differential pressure, concentration, polarization, and conductivity. And so recovery is going to be how much permeate water we're producing from our feed water, right? So if we have 100 cubic meters per hour of feed going into our system, we're producing 75 cubic meters per hour of permeate or clean water. We have a recovery of 75%. Now, the water that's rejected is going to be our brine or our concentrate water. And this is going to be the difference between the feed and the permeate. So we can think of it kind of as a mass balance where we have one stream entering and two streams leaving the system. One is our product and one is our waste. And now related to this, and this is very important, is our concentration factor of the system. So as we start to produce more water, we're going to start to leave behind more and more of these salts. So we can actually calculate how much we're concentrating of these salts using this formula here. This is our concentration factor formula. So what this means is, as we start to increase our recovery, like I said, we'll see kind of this exponential growth curve of how much we're concentrating in our system, right? So if we look at 75% recovery, for example, we have a concentration factor of 4. And if we increase all the way to 90% recovery, we would actually have a concentration factor of 10. So what does this mean? Let's say we have a feed sulfate concentration of 50 parts per million, right? At 90% recovery, this means we're going to have about 500 parts per million of sulfate. And if we increase just a little bit further, just 8% more, 98% recovery, we're going to increase all the way to 2,500 parts per million of sulfate. So this is really important when we start playing around with the recovery of our system. We have to keep in mind that we're also further concentrating these solids in our water. So another really important parameter in these systems is going to be flux. And flux is the amount of water that we're producing in a given surface area, right? So these membranes have a fixed surface area, usually around 400 square feet of material that they can use to produce water. And many membrane manufacturers will give a recommendation of how much flux these systems should produce. So if you ever look at, maybe a Film Tech model membrane or a Toray model membrane or a Man and Hummel membrane, you'll see that the water that is produced is going to be set and fixed for certain types of water. So wastewater, for example, might have a bit of a lower flux recommendation than something like a well water. And this is also something that we can easily calculate. The crossflow velocity is also a very important parameter to consider with these systems. So the amount of water that we're flowing through the system will result in a velocity through the system, right? And in order to prevent scaling or biological accumulation in these systems, we want to make sure that we're also having enough turbulence to flush all of these salts and scales and organic matter from the system itself. And in order to help support that, we can actually play around with how much flow is going through the system in order to increase this velocity. So a lot of times we'll see minimum concentrate flow rate recommended, and this is the way that we know that we're achieving a proper crossflow velocity in our system. And here I have just some information about some very standard recommendations for different sized elements and their maximum fluxes, like I mentioned, and their minimum concentrate flow rates for different types of water. So you can see, depending on the water source, we have some different recommendations. Now, another thing I want to talk about is a differential pressure in these systems. So like I mentioned, we're applying a pressure at the feed in order to produce water, and we'll start to lose some pressure through the system as we, produce water and lose some pressure due to flow restrictions. And this is a natural process that will happen, but it can also be increased by things like scaling and fouling. So here you can see we're flowing water through our pressure vessel, but as we start to accumulate some scale or foulant, we can start to restrict that path of flow. And then this can cause an increase in our pressure drop or differential pressure. So you might have a much lower pressure on the second image on the bottom compared to the first. And now I really quickly want to touch upon the composition of feed water for these systems. Like I mentioned, we're trying to target the removal of these different substances. So these are things like calcium and magnesium, which are hardness, or bicarbonate or carbonate ions. And a really good way that we can measure this is through conductivity. So if we take a sample and use a conductivity probe, we can get a reading that can give us a good idea of how much of these dissolved substances are in our water. You'll also often hear the term total dissolved solids, like I mentioned, and this will be another form of measuring the total concentration of these different salts in your water. And now this is going to get a little bit more complex. The idea of concentration polarization is also a very important phenomenon to consider in these systems. So again, like I mentioned, as you're flowing water across your membrane and producing clean permeate water, you're going to start to leave behind a lot of these salts that we want to remove. And as you start to remove these salts, you start to get this much more bulkier, more concentrated area very close to the membrane surface. And this is actually where scale can start to form. So as we become oversaturated in things like calcium and phosphate and sulfate, we can start to form different types of scales that can ruin the performance of our systems. So we have to be really careful that we're considering all of these different, phenomenon and parameters to make sure that this is avoided. And here I have an image of, a membrane that actually has some silts and particles accumulated on it. So all of these different, dirt particles were trapped on the membrane, unfortunately. And what I want to show here is that pre-treatment for these reverse osmosis systems is really, really important. So like I mentioned, they're really targeted to remove these dissolved substances, and we want to avoid any of these larger particles from being able to plug the system up and prevent water from being made. So again, like I mentioned, it's just very important that we're considering, what is in our water, what pre-treatment we have to our systems in order to make sure that our reverse osmosis systems are operating as best as possible. And so here we just have a little bit of a design, an example design where we have different types of pre-treatment. So maybe like ultrafiltration or multimedia filtration in order to remove these different particles before reaching our reverse osmosis system. And another really key part of this pre-treatment that I'm talking about is the use of anti-scalants, which Danny mentioned is something that we provide along with Higricon in order to help protect these reverse osmosis systems from losing their performance. So it's really important that we select the right anti-scalant depending on what type of system you're using and what type of water source you're using in order to help them perform their very best. And so now I'm going to really quickly go into how membranes actually scale and what we can do to control them. So there's many different types of scale that exist. Very commonly, you might hear of calcium carbonate scale, but there's also types of scales that are sulfate-based, phosphate-based, silica-based, and you can even have scaling from the anti-scalant itself. So it's really important that, the people operating the systems and designing the systems have a good understanding of which scales are of concern for a given system. And so here I have some images of the different types of scale, but you can see that they behave a little bit differently from one another. So again, the type of chemistry that you're using in your anti-scalant is really important in order to target each specific type of scale. And so I'll go into it in a bit more detail in a few slides, but I'm going to discuss our anti-scalant projection software, Proton. And so this is going to be a really good tool that you guys will all have access to in order to see, what scales are going to be of most concern for your system. These are all calculations that will be done automatically as long as you give a feed water quality to the software. And we'll be able to take into account all of these different parameters like the fluxing of the system, the concentrate flow rate, the concentration polarization. All of that will be taken into account with this software. And so background as to how antiscalants actually work. There's four main mechanisms. And like I mentioned again, each different type of antiscalant will use one of these four mechanisms in order to prevent the different types of scale. Another really important thing to consider is that the antiscalant is being dosed properly. So again, this is always something that AWC along with HEGRCON can help support in order to make sure that the correct antiscalant dosage is being used to properly control the scale in the system and make sure that the system properly. So one really good way of doing this is a drawdown test where we double check, the amount of volume that's being used in the system, and we can make sure that the proper dosage is being used that we're recommending. And so, like I mentioned, there can always be an issue of overdosing your antiscalant. Many times in the field, we'll see, a system might have an issue and an operator might think it's a good idea to maybe just dose a bit more antiscalant in order to help control the scale. Unfortunately, this isn't always the solution. So we can actually run the risk of forming this antiscalant salt that you see here. This is an image from our lab again, where the antiscalant itself forms a scale. So this is something that we take into consideration at AWC, and we can actually assess for this potential with our antiscalant potential or antiscalant precipitation index. So again, at AWC and with HEGRCON, we're always trying to make sure that the system is operating as best as possible, and we're always giving the best recommendations that we can. And so now I want to talk really briefly about organic foulants and biological fouling or biofouling. So oftentimes these are kind of grouped together as the same type of issue, but they're actually quite different. And also to the naked eye, they might look a little bit similar as well. Here on the top image, you can see we have organic fouling, and on the bottom image, we have biological fouling. So to the naked eye, it might look like the same exact thing, but biofilm or biological fouling is actually going to be alive and allowed to grow. So it's going to be a bit more of an issue than organic fouling, which is made of the things that are already dead and decaying. Biofilm, like I mentioned, is going to be alive. It's going to consist of not only the bacteria themselves, but also this kind of matrix, this gooey substance that it forms around it in order to protect itself. And when we talk about reverse osmosis systems, like I mentioned, we have hardness in our feed water, right? All these different dissolved substances can actually impact the biofilm itself. So calcium or magnesium, for example, can help to stabilize the biofilm and make it a lot harder to remove. So with this in mind, it's really important that we're always using the right chemistry in order to remove this complex kind of fouling that's formed and make sure that we're really targeting what the issue is at hand. And so now I'm going to go into our projection software a bit. Like I mentioned, this is free of charge. We have the link to register right there in the QR code, but I'm sure you guys will also all get a link afterwards. And so the way that this software works is that you put in a feed water quality, like I mentioned. You'll design your reverse osmosis system or just put in the details of the system that's already designed. And then Proton will give you an idea of what the permeate water quality is going to look like. So the clean water. It will also give you the idea of how much scaling potential there is in the system. And then it will also give you recommendations on the anti-scalant you should use and the cleaners as well. So this will be targeted for your exact system. So here I'm showing the very first kind of bit of information that you would put in. You can see here we can put in a lot of detail for the feed water. We can put in the different ions like calcium, magnesium, barium. If you have even lithium in your water and you're working with a more industrial process, we have the option to add all of those details here. And this is going to become really important in the calculations that Proton will do in order to determine what scales are of concern. So here we have a little screenshot of the part where you design your system. So again, you'll be able to put in the details of how many pressure vessels you have, how many, membranes are in the pressure vessels, what type of membranes you're using. And then from there, you can tell Proton how much you want to recover of your water, how much feed, so that you can really exactly to how it is. From this point, you'll be able to summary of the permeate water that you're producing. Here you can see we have our permeate water, our reject water, and you'll also be able to see all of the scaling potentials for the water as well. So here we have all of our main different scales, and Proton will tell you how well each one of these scales is going. Not only that, also give you a very nice summary of the recommended anti-scalant, like I mentioned, the dosage that it recommends you to use it at, always at the lowest dosage because we always want to try to reduce OpEx costs. And it will also give you targeted cleaners in order to help remove these scales and foulants. Another nice little feature that we have on Proton is the ability to simulate post-treatment and assess for different types of post-treatment. So if you ever have any post-treatment that you want to assess for, whether it's chemical stabilization or degasification, this can also all be done from one software. And then from there, Proton will give you a very nice summary of all of the chemicals that you're using in your system, that you're consuming over time. And then if you have information on pricing, you can also put that in and see how much it's going to cost you over time. If you also have information about your high pressure pump, for example, you can see how much the pumping is going to cost itself. Because like I mentioned, these systems rely on very high pressure pumping in order to produce water. And so I don't know how much time we have. 10 minutes? I think this might be a good place to stop this next session. Yeah? Okay. So I think we'll continue after the break, which we're going to take now. Perfect. We'll see you soon.
Zahvaljujem se gospođici Gabriele Brumer na njenom izuzetno korisnom izlaganju i podijeljenim stručnim iskustvima. Ovim završavamo ovaj dio programa, te vas sad pozivam na kratku pauzu. Nastavak radionice nakon pauze prema predviđenom rasporedu. Osvježite se malo, ima voda, sok, kafa i mala zakuska. Malo priča, malo nesumno.
just how do I do microphone? Microphone is you click on this.
Speak. Nakon pauze program nastavljamo izlaganjem Gabriele Brumer koja će govoriti na temu napredna hemija vode, prevencija skaliranja i razvoj protokola za čišćenje reverzne osmoze i nanofiltracije membrana. U ovom predavanju biće poseban fokus na praktične pristupe kontroli naslaga i optimizaciji hemijskih režima s ciljem očuvanja performansi membranskih sistema i produženja njihovog radnog vijeka. Please.
Okay. So now we're going to change the subject just a little bit, and we're going to talk about how we can actually tell if our systems, these reverse osmosis systems, are performing well. So there's a lot of different things and parameters that we can track in our reverse osmosis systems. Like I mentioned, we have temperature, we have pressure, flows, conductivities. And if we're looking at all of these different trends and graphs all at once, it can be a little bit confusing, right? So here we have an example of all of this raw data all put together on one graph, and it's hard to tell if the system is working well or not. So the way that we can make this data a lot easier to interpret is by collecting the data and normalizing it. So when we normalize data, we're taking all of the information from the water quality, the pressure, temperature, and recovery, and we're able to kind of make this standard and see how these different changes are affecting our performance in terms of scaling and fouling. So here we have an example of the way that we're able to take all of this raw data that looks a little bit crazy and actually normalize it into a single graph that we're able to use to see how our system is performing. And so this process can be a little bit complicated. I'm going to walk you very quickly through some of the formulas that we use, but luckily all of this can be done through different types of software that make all of these calculations automatic. We'll just put our raw data in, so our pressures, our flows, conductivity, and then we'll get all these different types of graphs out that are able to show us our system performance. So like I mentioned, we're going to standardize for the effects of temperature, changing concentration of our dissolved solids in our feed, and the different feed flow rates, which then affect our permeate flow, the amount of salt that's passing through to our permeate, and the amount of pressure drop that we see across the system. So these are going to be the three main things that we look at to know if our system is working well. And so here we have an example very quickly of how feed pressure can actually change with temperature, just as a very basic example, right? So as we increase our feed temperature, our water becomes easier to flow, so we need a little bit less pressure in order to produce water. When we do this process of normalization, like I'm talking about, we're able to remove all of those effects from things that we can't change, like temperature, and we're able to see really how the system's performing. So here now we see our normalized permeate flow, which is something that we're tracking, is actually stable, even though we have this change in pressure and temperature. And overall, this will help us troubleshoot how the plant is going to perform. So like I mentioned, these are the three different main performance kind of parameters that we want to track that are normalized. I'll go very quickly through this just because we're running a little bit low on time. But like I mentioned, temperature is going to be a very big impacting parameter on our system's performance. So at higher temperatures, we're going to have higher viscosity, which means that lower viscosity, which means that our water is a lot easier to flow. So at lower temperature, we're going to have the opposite effect, higher viscosity. So we can think of something almost like honey, right? That's very thick. It's very difficult to flow. The same thing happens with water. So if we drop our temperature, we're going to start to see this effect change in our system because we'll actually start to produce a little bit less water of our permeate. But this is just natural effect. This doesn't necessarily mean that our system is scaled or fouled and losing performance. So it's something that we have to account for. Net driving pressure also is something that we need to take into account when these different calculations are being done. And overall, it turns into this crazy looking formula that luckily we don't really have to deal with, because a lot of the software that we work with will do these calculations for us automatically so that we can tell if our systems are performing well. Differential pressure, like I mentioned earlier, is also something that we can monitor, and we can also normalize this in terms of different things like flow and temperature to see what the true effects of scaling and fouling are on our system. So here we'll see these effects of DP due to scaling and fouling when we have clogs in the system feed, like you can see here in this image, or as we start to develop kind of a film on these feed spacers that I was mentioning before. So again, we're reducing the ability for water to flow through because of scaling or fouling, and this is going to show up in our normalized differential pressure. And here I have an example of how this effect of normalization actually works. So on the top graph, we have the recorded or observed differential pressure. So these are just the values that we're measuring on site. You can see that both of our graphs, or both of the trends on the top graph, are showing very high increases, which makes it look like our system is performing very badly. But on the bottom graph, once we do this process of normalization, everything is a little bit flattened. So we're taking out all of these effects, like I mentioned, of flow and temperature, and we're seeing what the true performance of the system is. And then again, here we have kind of this crazy formula, but luckily, all of these normalization softwares are going to be able to do this process automatically. And now the third parameter that we want to track is the normalized salt passage. So this is a salt that's actually allowed to pass through to the permeate side of our water, and it increases our conductivity of our permeate or produced water. So these changes in salt passage can happen due to fouling, scaling, halogenation, and other types of events like mechanical damage. So when we do this process of normalization, this is what we're looking for. We want to see if we can identify any of these different phenomenon in our system and try to troubleshoot what's happening. And so again, these are impacted by things that we can't control, like temperature or just the natural quality of the water that changes a little bit over time. So if we're just looking at raw graphs, it might look like our system is performing badly, but once we do this process of normalization, we can really see what's going on in the system. And here we have another one of these crazy kind of formulas that, again, luckily the software does for us. Here I have an example of the salt passage before it's been normalized. So you can see over time, we're seeing this very high increase in salt passage. It makes it look like our system is not doing its job in removing salts, right? Once we do the process of normalization, the true performance of the system is actually very good. So now the red line is this normalized data, our normalized salt passage. And it turns out that the system is doing its job, and likely the blue line was just due to effects of temperature or changing water quality. So here we just have kind of a brief summary. So you know that if your temperature increases, for example, if you're looking on site, you're going to have an increase in permeate flow or an increase in salt passage. Same thing with increasing recovery, so how much water you're producing. You might see an increase in permeate flow or an increase in salt passage. But once we take a look at the normalization, we'll really be able to see what's going on in our systems. So now collecting this data is also a very important process, right? We want to make sure that we're tracking the right parameters in order to actually be able to do these calculations. We also want to make sure that all of the meters that we're using for these, readings are also very well calibrated. The amount or the quality of the data that we're putting into our process of normalization is really important for the quality of data that we're going to receive from this process. So here we have an example of an actual site that was watching their normalized permeate flow. They saw that they actually dropped in normalized permeate flow, so their amount of water that was being produced, in half. And this was a very quick change that you can see. And what actually happened was that they just recalibrated their conductivity meter. That, making sure that your instruments are reading correctly at the right times, important process in this whole data collection process itself. It also matters very much how often you're collecting this data. So very often these systems will be collecting data automatically, or we can have operators on site and measurements to make sure that they're trying different raw parameters. So recommended ideally once per shift before and after any process changes, so we can see if we do make any in our system. And so here I have just show exactly which parameters are ideal to track. So like I mentioned, we want to look at our feed flows, temperatures, conductivities, and pressures. Same thing with our produced water, the flow that's being produced, the conductivity of that clean water, and the pressure as well. Same thing with our reject or waste. And so this process of normalization can be done per stage. So this will really be able to tell us what's happening in each one of these stages of our reverse osmosis systems. It might be that the problem is in the first stage versus the second stage. So when we're normalizing or collecting data by stage, it can really tell us a lot about what's going on. And so here I have another little list of, all of the different parameters we'd want to track, for example, for a two-stage reverse osmosis system. And while it does look like a lot, we can actually do a bit of mass balancing and kind of reduce the amount of parameters that we're needing to track, right? So our concentrate flow from the first stage, for example, might be just the feed flow for a second stage. So we might just need 1 meter in order to record multiple different parameters. The normalization process can also be done for the system as a whole, so that you can take a look at what's happening through your entire overall system. This can make it a little bit more difficult, unfortunately, to tell exactly what the issue might be at hand. So whether the issue is mainly scaling or fouling, which happen in 2 different parts of the RO normally. But if you want to help save money, oftentimes this is done in order to reduce the amount of meters or instruments that are used in order to collect the data. And so another really important part of this process of normalization, like I mentioned for performance tracking, is documentation. So we want to make sure that we're getting context to the different changes that we're seeing in our system. So whether we're doing, maybe changing our source water, maybe we're changing from a well water or a municipal water, this can impact the way we're seeing our trends. If we're doing cleaning events, so we're cleaning the system, we might see an improved performance. Or if we're doing any type of maintenance on our system, this is also very important. So we have context, like I said, of why something is happening. Here, for example, we have a trend of this normalized permeate flow, which is our produced water. And after each of these yellow lines, we saw performance improving. And when we went back and looked at, the historical data of what was happening at this site, it was actually that this site was doing CIPs or cleanings, and this was able to be matched to how their system was improving, right? And now, another really important part of this process is understanding how to actually deduce what's happening or understand what's happening from these different trends. So there's a few different trends that should raise actually a red flag to us. So if we see something like a loss in normalized permeate flow, or an increase in salt passage, or an increase in normalized differential pressure, this can mean that something's happening in our system that we don't want, and we're actually losing performance. So as a rule of thumb, if we see kind of a decrease in normalized permeate flow of about 10%, this should trigger a cleaning of the system. Same thing with normalized salt passage, increases of 5 to 10% also should trigger a CIP or cleaning, and an increase of normalized differential pressure of 10 to 15% as well. And the main parameter, because I've mentioned 3, the main parameter that we really want to track is how much water that we're actually producing. So the normalized permeate flow. This is going to be oftentimes the very first indicator that something's going wrong in our system, that we're having some kind of fouling or scaling event that we need to take care of. Normalized differential pressure, right, is going to be kind of a secondary indicator for cleaning, but it can often tell us a lot about maybe what's going on. And same thing with the normalized salt passage indicator. And if we allow the systems to pass these thresholds of, 5 or 10 or 15% for these different parameters, a lot of times the foulant or scale can actually become so bad in the system that it can become irreversible and the membranes might need to be fully replaced. So it's really, really important that we're making sure that the system is healthy and we're cleaning and taking care of these membranes when they need to be cleaned. So we have a few different processes for when we're investigating what the issue is on site for these systems. We can confirm that we're dosing the correct chemicals, that we're analyzing the feed water, making sure that there's no significant changes in how much hardness there is or alkalinity. We can weigh the membranes to see if there's a very heavy weight and if there's maybe a little bit of foulant that has accumulated on it. Or we can do an autopsy on the membrane, which is something that AWC provides and offers to see exactly what is on the membrane itself. So when we're dealing with organic and biofouling, these symptoms are going to kind of present themselves differently than scale, right? So organic and biofouling is going to mainly be observed in the first stage or the very first stages of a system. Here, we'll start to see our normalized permeate flow decrease, again, mainly in the first stage, as these are kind of foulants that are trapped in the lead elements of a system. And we'll start to see an increase in normalized differential pressure. And this is because the foulants or biofilm will be allowed to grow and again, reduce the amount of flow that's able to pass through the RO itself. The second stage that you might notice here doesn't change too significantly when we're seeing organic or biofouling issues. So again, this is why it's very important that we kind of track the information for each stage individually if we're able to. And here I have some kind of gross pictures, but these are examples of organic and biofouling events that happened on reverse osmosis systems. Oh, and there's no images there. There are a few risks, like I mentioned, of operating above the kind of thresholds for these different normalized parameters that I mentioned. So when we operate with high differential pressure, for example, we can cause mechanical damage to the system itself. So we can start to break the fiberglass shells. If we're operating with too high of differential pressure, you can start to see the feed spacers protruding from the end of the membrane. So these are things that we want to avoid, and that is why it's very important that we're watching our normalized data. Now I'm going to talk about scaling. So again, this is a little bit different from how we look at organic or biofouling. Scaling is going to mainly happen in the tail elements of our system where we have very, very high concentrations of salts. So when we're looking at our normalized data and we're suspecting scaling, we're going to see this decrease in normalized permeate flow mainly on the second stage. Also, we're going to often see increases in normalized differential pressure in the second stage. And so this is because as the scale begins to form, like you can see, it will actually start to clog the active layer of the membrane that's able to produce the water, and this is going to reduce our performance capabilities. And so there's a few different types of scales that will present itself in different ways. But of course, this is always something that an expert, membrane expert, can help you assess to determine exactly which type of scale you're dealing with. Now, when we talk about normalized salt passage, because I haven't talked about it too much, there are a few different ways that we can see increases in this parameter specifically. So the membranes could be potentially damaged chemically or mechanically, and this can result in increases in salt passage. We need to make sure also maybe our instruments aren't working correctly. So like I mentioned, we want to make sure that the conductivity meters are calibrated and they're working correctly. And if those aren't the reasons, we can start to look into other, options of why the high salt passage can be occurring. So one example of this mechanical damage is the end cap adapter. So like I mentioned, we have this nice thin little tube that collects all of the clean water in our systems. And if there's a little crack in it, we can have some concentrated water leaking into the clean water. So this can be kind of an example of why we would see an increase in salt in our clean water itself. So it doesn't necessarily mean that our system is fouled or scaled. It's just something mechanical that can be fixed in another way. We can also do a few different types of tests like pressure vessel profiling. So here we can take a look at, are all of my pressure vessels working the same way? Maybe if I'm taking a reading of my conductivity in one of my pressure vessels and it's a lot higher, like the 72 microsiemens here, we know that we have an issue specifically in that pressure vessel. The same thing can be done within the pressure vessel itself, right? So like I mentioned, we might have a broken kind of crack within that permeate tube. So a good way of checking that is by doing a test like membrane profiling. So this can kind of show us if there's any spot where there's damage to the tube itself. And here we'll be able to tell exactly where through a test like membrane profiling. There's a few other reasons for high salt passage that we can see. So if we actually damage the plastic membrane layer itself, this can result in irreversible salt passage that we can't prevent or reduce. So like I mentioned, these membranes are very, very sensitive, and any back pressure that we apply to them can be very risky, and it can actually damage the layer that's doing all of the salt separation. Here we have some images of this, kind of phenomenon when it's occurred. So these systems unfortunately had some back pressure on their reverse osmosis systems, and this caused that active layer to literally blister and crack off. So this was a very severe example, but you can see here, this is why they were experiencing this increase in conductivity in their permeate water. And here's another close-up image of that blistering kind of effect on the membrane itself, which is what we would want to avoid. Different types of chemicals that are used in pretreatment also can potentially be incompatible or not work very well with the membrane itself. So again, like I mentioned, these membranes are very sensitive to different chemicals. So it's really important that you work with the membrane manufacturer to make sure that everything that you're using in your pretreatment is applicable and membrane compatible. So some types of chemicals like chlorine dioxide or ozone or hydrogen peroxide that are often used for disinfection can actually damage the membrane and cause it to be irreversibly damaged and have very, very high salt passage, which really defeats the purpose of these reverse osmosis membranes. So this is something that we always want to consider and try to avoid. And now with that in mind, all of this kind of information is being used to know when to clean. So if we have scaling or fouling on our systems, we want to make sure that we're cleaning on time. And this can be done by using our normalized data, right? So here I have an example of, normalized permeate flow that we were tracking for a customer. You can see that we were marking this red line, which is that 15% decline, which is when we know, okay, the system needs to be cleaned. And each cleaning was able to restore performance, but in some cases it wasn't able to restore performance as well. So in the purple area here, we're able to get back to that target performance of 400 gallons per minute production. And this is because the cleanings were being done on time. It was being done before we were hitting this red line of 15% decline. In the blue section, here we were allowing the system to go drop below this red line, which is kind of our threshold for when we need to clean. And here we can see that these same cleanings that were being done weren't able to restore performance as well. So this means that the scale or the foulant was able to become so severe that maybe a stronger or more severe cleaning was required in order to fully remove the foulant and get our production back to where it needs to be. And so now for this last portion, I'm just going to go over some kind of tips and strategies on how to actually clean our membranes when we do see performance decline. So like I mentioned, we have a couple different types of biofoulants like bacteria, algae, fungi, which all behave very differently. Same thing with organic foulants, right? We have dead bacteria, we have decaying vegetation, oils and greases, and all of these different, constituents can come from different source waters. And so it's really important that we understand exactly what's on the membrane so we can recommend and use the best cleaners as possible. And so ideally, when we're doing a cleaning, there's a few different kind of points that we want to make sure that we're reaching. So when we're cleaning specifically for biological or organic foulants, we want to make sure that we're using a high pH cleaner, high temperature that can, be used for the membrane. We want to make sure that we're still applying what the membrane limits are. We want to make sure that we're cleaning with a high flow rate and that we're periodically soaking so that we're able to really penetrate that foulant and make sure that we're able to fully remove it. And so removing biofilm from RO systems can be done in a few different ways, right? Like I mentioned, we can use high pH cleanings. So this cleaning solution of, maybe 11 or 12 pH. We can also use chemicals like surfactants. We can use chelants like EDTA. And we can use oxidants. But we have to remember these need to be membrane safe because they can cause membrane damage. Another consideration that we need to have when doing these cleanings is that sometimes these cleaners can cause foam. So this is something to note on site when we're doing the cleaning in case there's any kind of risk of foaming on site. Now, when we do these cleanings, we can target high or low pH to remove different substances. So high pH is going to be targeted towards the biofilm or organic foulants, and low pH we can also use. And this is going to be targeted more towards things like scale, so calcium carbonate, calcium phosphate, things like that. It's really important that we understand how the low pH cleaner can actually work with organics and maybe actually make it worse. So at AWC, for example, we recommend that high pH cleanings are done first because if you're using a low pH cleaning on organics, it can actually cause everything to compact and then make it a lot more difficult to remove. So the way that you're doing your cleaning for these systems is very, very important to make sure that the cleaning is effective. Another thing to note, like I mentioned, is the temperature of the solution, right? So this has to kind of do with the kinetics of 5 minutes? Okay, cool. So this kind of has to do with the kinetics of how the cleaning is performed. At higher temperature, everything is going to move a little bit faster and the cleaning is going to be more effective. The flow rate also is very important, so we want to make sure that we're fully shearing off all of the foulant as best as possible. Many different membrane manufacturers recommend different cleaning flows for their cleaning processes in order to fully remove all the foulant, like I mentioned. So these are the targets that we generally recommend at AWC in order to get the most effective cleaning possible. And then, like I mentioned, different things like the flow direction can be modified in order to get better cleanings. The soaking time also can be modified and played around with to get better cleanings. So here, for example, you can see a study that we did where we circulated and soaked the cleaning chemical over different times in order to get a better cleaning on this foulant. And for sake of time, I'll just pass through these very quickly. All right, and then for inorganic scales and precipitates, like I mentioned, so these are going to be scales like calcium carbonate, sulfate, silica. Each one of these different scales is going to require a different targeted cleaner. So again, it's very important that we understand exactly what's on your membrane so that you're able to best remove the foulant or scale itself. So again, very similar to the organic cleaning strategies, we recommend for low pH cleanings for scale that you're using that low pH targeted around 2, that you're using also high temperature, high flow rate, and making sure that you're cleaning for the right amount of time. And so I'll just pass through this very quickly for sake of time. This one here? Okay, perfect. So like I mentioned, we need to make sure we're cleaning also for the right amount of time, right? So oftentimes our customers will tell us, okay, we cleaned our system for 4 hours and we didn't see that the chemical did its job. Well, here you can see that, we cleaned their same system for 4 hours with the same chemical. And if they had cleaned for just a little bit longer, they would be able to really fully remove the foulant. So if we're cutting our cleaning short, we might be leaving a lot of that foulant still on the membrane surface. And then when we start our system back up, we might still see those effects. So AWC generally recommends that cleaning is done for 6 hours at high pH and 6 hours at low pH. So this is going to be able to ensure that all of that foulant is fully removed. Another really important part of optimizing the cleaning protocol is using the right chemicals, right? So here we have an example of an actual plant. So this was a desalination plant, and they were using EDTA at 1% at a pH of 11, 35 degrees Celsius for 6 hours. So they were reaching the right, pH, temperature, and cleaning time, but they were using a commodity chemical. And so here you can see on the very left side that there's still this very dark discoloration on their membrane surface, even after cleaning. And so this is all of the remaining foulant that was left on the membrane that wasn't removed by the cleaning itself. So we did a second test with a different chemical that wasn't very well suited for this foulant. And you can see that even though we're using a specialty chemical, it wasn't targeted, and we still have this very dark purple discoloration in the middle. Then when we switched to a third product, which is one of our AWC cleaners that was targeted for this foulant, you can see now that all that very dark purple discoloration here on the right is fully removed. So what I'm trying to emphasize here is that using the right chemical is a really important part of this cleaning process. It doesn't always make sense to just use caustic, for example, to clean a system. Done? Okay, perfect. Well, that's all the time we had for today. And yeah, thank you guys so much.
Zahvaljujem se gospođici Gabrieli Brima na izlaganju. Program nastavljam izlaganjem Arifa Karahilogulua iz kompanije Hummel, a predavanje na temu Dizajn Aqua Pro softvera, intuitivno projektovanje, optimizacija, reverzne osmoze, nanofiltracije, ultrafiltracije sistema. Welcome.
Hello, good afternoon. I'm Arif. I work for Manon Hummel since 2025, beginning of 2025. I live in Germany. Originally, I'm Turkish. I would like to ask first, is there anybody know Manon Hummel or they used Manon Hummel product ever? I'm asking is mostly well known in the car filters. Man filter is quite famous. I joined Manon Hummel. I didn't know. Yeah, but then since 2018 or even before, they joined the water business, because Manon Hummel is experienced and they would like to be a filter expert in every area. Thank you. Yes. As said, first I would like to start with what Manon Hummel is doing overall, and then I will go down to which segments and applications we are actively in the market, also in water, especially water treatment. And then I would like to talk about the products. At the end, I would like to show our projection software program, how you design your reverse osmosis and ultrafiltration systems. Yeah, Manon Hummel started in 1938. It started with the automotive business, as I mentioned, and then they grow, and now they are also actively globally in water treatment and wastewater treatment. Now with the more than 21,000 employees, and I would like to show how we invest in the research and development worldwide. Only for R&D, more than 1,000 people are working in our laboratories and all development processes. Overall, we have four main areas. Most of them belong to automotive or related to automotive transportation, but we are in this in water and membrane solutions. Stramatic is digital solutions, and Manon Hummel, as you see in that corner, is water treatment products. Milestones, how Manon Hummel joined in water treatment, water and wastewater. It's a little bit slow. Actually, in even before 2000, it started with the acquisition of Höchst membrane divisions in Germany, and then 2002, Microdin Nadir, which is a MBR membrane producer in Germany near Frankfurt, and then 2015, all the companies they acquired became under Manon Hummel umbrella. And 2019, we started to produce ultrafiltration membranes in China, Kunshan. Our production sites are in the United States, Italy, and Germany, and China in water division. Here you see on the map. These are all only dedicated for water production. These are the segments in where we are active. Wastewater treatment are one of the most focused treatment application. Food and beverage, milk industry is our focus also. We can concentrate protein, whey, and etc. Also in sugar applications, wine applications, we have special membranes. By the way, I put some cutoff products here. I suggest you in the break, maybe you can have a look. And during my presentation also, I will show you. And our biggest business in desalination, especially in the Middle East, from seawater to drinking water production, are done by our seawater membranes. But also in other applications like mining, drinking water application, chemical industry, we have brackish water. So the reverse osmosis membranes basically separated into two, brackish water and seawater. After the divisions, which areas are we active globally? In residential water, maybe, I don't know, in Bosnia, it's popular to kitchen size, small size membrane treatment for your drinking water from the tap, or commercial water from municipalities, and desalination application in drinking water production. For industrial solutions, we have processed water and ultra pure segments. Processed water is what you get to your factories from the well, from surface, from whichever the sources. And ultra pure water is quite popular now because of pharmaceutical applications and also semiconductor chip production applications. But basically, they are all the similar reverse osmosis membrane application. Pressure or like permeability, etc., are different, but it's basically the same product. This is one of the cutoff. They are as you can see, maybe not from there, but if you can look, it's a spiral wound reverse osmosis membranes, and in between there's a mill spacer, and this is what Gabi was explaining, the permeate tube in the middle. So the product water is produced from through this tube. Apart from processed water, we are quite active also in wastewater treatment plants, industrial or municipal. We are helping the tertiary wastewater treatment, which is kind of polishing after the conventional wastewater plants. We are active in coal mine wastewater treatment. They usually push, the states or regulations push to mostly zero liquid discharge from coal mine wastewater. In the slides, I will not talk about our all references and case studies, but I put them for your future references because we will share with you the presentations. And you will see our coal mine wastewater treatment case studies, oily wastewater treatment case studies, and the other one. And we have reverse osmosis, but at the same time, pre-treatment to reverse osmosis membranes is quite important. And we suggest mostly the ultrafiltration for pre-treatment. Still, I think most of the pre-treatments are conventional, scent filters, media filters, cartridge filters, etc. But with the ultrafiltration membranes, you can get, regardless of the feed water quality, always the same standard permeate water from ultrafiltration to feed the reverse osmosis, which makes it much longer duration lifetime for the membranes. And also you will see our case studies and references in our textile wastewater treatment application, landfill leachate treatment in some part of Europe and the Middle East. It's quite big industry, and our reverse osmosis membranes are actively used in landfill leachate applications as well. What is different is when you have more difficult water like landfill leachate, maybe also, yeah, from there, maybe it's difficult to see, but this spacer, mill spacer in between the flat sheet layers, it's getting bigger and bigger. However, how dirty is the water, the flow is much easier when you have the bigger mill spacer. But then you have to compensate from the whole flat sheet. But this is how it works because of the difficulty of the water treatment. Again, apart from municipal wastewater, also we are actively producing the products for industrial wastewater solutions, like tertiary wastewater, secondary wastewater. Also, we are helping with our membranes also the biological treatment in conventional to increase the capacity or improve the permeate of the conventional wastewater treatment plants. Some regulations are getting stricter and stricter. Even sometimes, or even usually, the conventional wastewater discharge is not enough, has not enough quality to discharge into surface water or even the sewage system. Then you have to polish that water, or even from the wastewater, you can use ultrafiltration and then reverse osmosis membranes maybe to use that water in your processes in your factory. Now, this is the overall. We are active also in microfiltration, but I will be focusing on Pure Ultra, this UF technology, and RO and NF technology in this presentation. This is overall, as a summary, our brand names. Pure Ultra, the first one is our hollow fiber ultrafiltration. These are sometimes they are called spaghetti ultrafiltration because of the shape. It's a hollow fiber pressurized ultrafiltration, it's called. We have Aquadin. It's not because they are mostly PVDF because of the resistant to chloride or other chemicals. PVDF is quite strong. But if there is a little bit of oil, which PVDF membranes cannot handle, we have also polyacrylonitrile PN Aquadin ultrafiltration membranes. It's a little bit different because of the material. It's resistant more to oil, up to 25-30 ppm, but it's working with a limited pH compared to PVDF hollow fiber ultrafiltration. We have ICEP and Spiracep, the third product. Which is this one. It's also spiral wound. It looks like reverse osmosis when you look at it, but actually it's a ultrafiltration. Its property is it's resistant to up to 1000 ppm TSS, which Pure Ultra and Aquadin or any standard hollow fiber membranes cannot handle, and also the oil content. We can treat up to 150 ppm oil with our spiral wound ultrafiltration membrane, this one. I will talk a little bit more in detail later. And of course, RO solutions and NF solutions. And Seprodin ultrafiltration is tubular. We are all producing them. Pure Ultra and Aquadin from China, ICEP from United States and China. RO solutions, we are producing them in Italy. And NF solutions, NF membranes also produced in Italy. First ultrafiltration product that I would like to mention is Pure Ultra, and we are giving warranty, especially with the turbidity 0.1, 0.2 ppm, and also 99.99 removal of particles more than 0.2 diameter, micron diameter particles. Where are these membranes used? As I mentioned, whatever the source is, wastewater, drinking water, seawater, surface water, after the pretreatment, prefiltration, you can use the ultrafiltration membranes for pretreatment of the reverse osmosis, and then reverse osmosis. If you, it depends on your needs. It can be 1 stage, 2 stage, or even further third stage membrane. But then you need to have higher and higher pressure, of course. But what helps you is to reuse more water, and also it will create less discharge water. This is also a summary. Pure Ultra, the first one, as a technical limitations, it's up to 100 ppm TSS. BOD and COD limits are also up to 100. Basically, 100 is quite high for hollow fiber ultrafiltration membranes, but also oil and grease is not, they are not really easy for hollow fiber membranes. That's why, as I mentioned, Aquadin, PAN membranes, because they can handle up to 25, even 30 ppm oil. And ICEP, the third product, it's for wastewater reuse, the one that I showed, spiral wound, but ultrafiltration membranes for up to 100, 150 ppm oil content in the water. It's quite unique. ICEP, the third product, is is really unique for oily wastewater treatment applications. I will not go into detail. These are all reference for you when we share the presentations. Our hollow fiber membranes are outside inside because there are two basic hollow fiber membranes. PVDF membranes are all outside inside. The filtration is from these spaghettis, let's say, from out to in, and the backwash is the opposite. But in the market, there is also PES, polyethylene sulfone, which is inside out, but it's not in our portfolio. We have three different types. If you have, is there anybody with the ultrafiltration membrane in the facility? Hollow fiber? Yeah. Sorry? Okay. These are, pressurized hollow fiber, but we have three different, and they can be replaced by other brands. We have this. We have the flexibility of the heads, this green color heads, and it makes you to be able to replace your existing ultrafiltration membranes when you have problem or over systems. We have 107, 80, and 60 square meter, depending on the capacity. Our hollow fiber there are three different production types of hollow fiber membranes: N-tips, T-tips, and M-tips. Ours is M-tips, which makes the polymer stronger in the hollow fibers. You can elongate those hollow fibers up to 150%. Because after a while, after backwash and air scouring, the fibers are broken time to time. But the stronger fibers you have, the lifetime is longer in your systems. Our fibers, as I mentioned, 150% elastic, which makes it the strength of the membranes. We have all the drinking water certificates, NSF certificates, Ministry of China, and halal certificates for reverse osmosis membranes and ultrafiltration membranes for drinking water application. This is also for you, for your interest later on. This is the scope of supply. All the connections are ready. And as I mentioned, if you tell us that which brand you are using in your existing ultrafiltration systems, we can one-to-one replace them. I'm mentioning it because ultrafiltration is not unlike reverse osmosis membranes. Normally, they cannot be one-to-one replaced without any modification of the connections. But we have this green head flexibility during the production. We can produce exactly the same type of other brands membranes. When we designed the system, our technical team in Italy and Germany, we give you this information, including like backwash pump, backwash capacity, flow rate, net flux, gross flux, and even electrical consumption of the systems. The references also for your future interest. It's not really updated. I will share with Nihat because it's up to 2024, but we have now also up to 2026. Overall, globally, in the United States, Australia, China, Europe, we have quite good amount of references for the ultrafiltration. Also, case studies, coal mine, textile, all those wastewater reuse, interesting projects we created. You can find them also in the presentation. I'm skipping for the sake of time. Textile dye reuse systems. Surface water treatment reuse.
Nee, Bayern.
Polyethylene is the second hollow fiber membrane, which is PEN, as I mentioned, polyacrylonitrile membranes. You will see in this one of the slides, the pH will be between 2 and 10, and PVDF pyrethrum membranes were up to, from 1 to 12. But the biggest advantage is oil content. Our case studies, even we have with the 35 ppm oil content in the water, but the more oil you have, the more backwash you would need. So the performance would be lower, of course. This is the compensation. But the important thing is the fibers are resistant to the oil, because PVDF hollow fiber membranes, for instance, they cannot be resistant. So it will be, they will clog in a very short time, which doesn't make sense. We have two types, 48 square meter and 65 square meter for PN ultrafiltration membranes. Also, we give all the design parameters to you. We can supply, and you can compare one-to-one with your existing system or with the competition. In India, I think this one should be 35 ppm oil. Yes, oil and grease feed water had 35 ppm, and then the permeate has 5 ppm oil content. I don't know why. In Australia, it's quite a big market for PEN. They prefer more PEN instead of PVDF. But for instance, China prefers most of the time PVDF ultrafiltration. ISEP and SpiroSEP, the ones that I showed, spiral wound ultrafiltration membrane. When you have a conventional wastewater treatment plant, and if you would like to increase the capacity, or if you add this ultrafiltration quality to reuse the system, or even if you want to add after the conventional reverse osmosis, the conventional wastewater treatment plant effluent would not be enough for feeding the reverse osmosis membranes because of very high STI and the other features. But we warranty with ISEP to have less than 3 STI value less than 3, so that you can easily fit the reverse osmosis membranes, and then you can reuse them in your process, for instance. Or even if you don't want to reuse it, your conventional wastewater treatment plant, let's say, are working over capacity, then we can, there are two types of this ISEP, one with the housing, one without housing. So, and if you have a footprint problem, you can also submerge this membrane into your existing tank, and then you can vacuum the clean water out of it. Because this ISEP and SpiroSEP, they are working without pressure. It's vacuum operated membranes. And because of the spiral wound and very high thick mill spacer, I will show you the photo. You can handle up to 150 ppm oil, which is quite interesting and unique in the market. Or if you have an MBR system, even most of the MBR systems in the world, I think, working over capacity because of the population migration to the cities. The shortest way of increasing the capacity of the existing MBR system, you can also use ISEP without any investing big amount of money. Then it will help your existing tank. And as I said, it can be outside with the housing or within the tank inside. Yeah, this is the technical reason why, one of the technical reasons why it's resistant, because of the interesting shape of this mill spacer between the layers, and it's quite thick and wavy, let's say, so that the oil or other particles can flow easier than the other membranes. I would like to show how we provide. It's 27.4 meter cube. For like a rule of thumb, if the water has 100 ppm oil, let's say, you can produce 1 cubic meter from one membrane per hour. So maybe if you have huge systems, it won't be feasible, but small to medium size conventional systems, you can increase your capacity or increase the quality of the effluent with the ISEP or SPIRESEP. The only difference is with housing, without housing. It's the same membrane. This on the left one is submerged into wastewater tank, and with the housing is next to the tank, outside. This is how we supply the product. And this number 6 is the diffuser. We also provide with diffuser because you need air squaring, constant air squaring, and you just need to connect it to blower. And this is the one without housing. Also with number 2, air diffuser we are supplying, and air blower should be connected to there. We also do our design. If you share your parameters, your wastewater content, we can design the flux and the number of modules that you need. And it's not really complicated. If you know the other ultrafiltration systems, you just need a backwash and chemical, like standard chemicals, alkali, caustic, and chloride to do CIP cleaning time to time. Yeah, we just won, apart from all this list, we just won in Iraq with the gradient around 1,200 pieces of ISEP, because it's surface water, but it's just next to the refinery, and there's a big amount of oil content in the surface water. And to reuse that water, they tested a lot of different membranes, ultrafiltration membranes, but ours has the longest lifetime and the highest quality of permeate. So it will be the biggest reference in our list. It will be 1,200 ISEP modules, which will start installation end of this year. Yeah, these are the ones. Not only it doesn't have to be really high content of oil, but chemicals, bacteria, etc., difficult water, let's say, you can use ISEP in your systems. Cooling towers can be also quite tricky because of the bacteria and chemicals. And all these are the reference list, case studies. For you to, yeah. STP effluent for especially summertime when the population is increased. When you have existing STP, it's problematic in Greece, Italy, because of the tourism, because of the population, and they can be used also to increase the capacity, as I mentioned before, and this is also one of them. This one is for tourism population increase. Yeah, so I'm done with the products. Basically, I will show the software, projection software for reverse osmosis and ultrafiltration. But if you have any questions so far about the products, I would be happy to answer. Okay. It's not a presentation. Open the program. Yes. You can download it in our web page. You just need to register your name and company, and in 1 or 2 days you will get the link for installation. And when you open do you use any kind of projection software from other brands also, like Wave or Rosa in the past, etc.? Okay. So this software program is to give you idea when you use reverse osmosis or ultrafiltration membranes, what would happen in 3 years, 5 years, etc., how you wish. And with the different temperature, different feed water quality, and what will your permeate water quality will be. This is the basic. Of course, at the end, how many membranes you would need, what and etc. But also it gives you the flexibility because you can change them as you wish according to your experiences. So in your an additional target is when you have existing reverse osmosis system in your plant to compare with the existing membranes, what would happen if you use the other membrane, for instance. And so it can give you to decide which brand you should use or which type of the membrane you want to use. When you open the program, this will be the first page. On the right side, you will see the list of your previous projects that you saved, and then you need to choose which one you would like to do projection: reverse osmosis, nanofiltration, or ultrafiltration. Let's start with the reverse osmosis membrane. I will not go into detail a lot because it has a lot of parameters, but I would like to show how, like which button is working for what and what kind of information you will get from the program. Yeah. And I would like to mention for reverse osmosis membranes, they are always one-to-one replaceable. Like any kind of brand in your pressure vessels, you can just take it out and put another brand reverse osmosis membranes. So you don't have to be dependent on any brand. And as Manon Hummel, we have all the range, I would say. So a high rejection brackish water, low rejection and high productive brackish water, and also seawater membranes, etc. You can choose. What we would need, either the existing system information, or you can just tell us we are using this model from this manufacturer, this model membrane, and then we can choose ourselves our equivalent membranes for that. And at the same time, of course, the more information is better. If we know the existing system, like how many stage, how many pass, how many pressure vessels, and etc., we can show also the comparison to you, and then you can decide better with that. So this is the first page when you choose reverse osmosis and nanofiltration. What would you need at the beginning? I think you can just for your future reference, let's say, you can use your project name, and in the later on when you open the file, you can with one click you can get back to your system. You don't have to start from the beginning as logic. So this Sarajevo will be seen. It's a little bit late. This Sarajevo will be seen in the main page when you open the program. Then the critical point, what is the source of the water you need to choose? If you are using well water, if you are using surface water, filtration, ultrafiltration, or conventional media filter, let's say, you one of them, or wastewater with ultrafiltration or seawater. This is critical because if you would like to see after 3 years, 5 years, what will happen, this source of water will be effective on the salt passage increase or pressure increase, and etc. That's why it's quite important. Let's say you just have well water and you want to treat this well water. In this list, these are the ones that you saved before, you used. Seawater. Yes. You can choose seawater after ultrafiltration, microfiltration, or just conventional media filter. And then it will be a little bit easier because seawater usually in this range, in the Mediterranean Sea, let's say 40,000 or sometimes it's 42,000, or in Red Sea, it's even more, a higher TDS. And you can choose one of them. Or you can create your own water analyze. It's also critical for brackish water. I would like to show, instead of just choosing from the literature, here, because of, you don't see, but there's a one screen in front of the buttons. I cannot go. Yeah. So what is critical is the ions. It's the beginning on basic of all water treatment plant, actually. The more information is better, as always. Anions and cations, most of the time, mostly sodium and chloride are the most critical ones, but the other ones are also needed to get the real osmotic pressure here, because this will change everything with the feed about the feed pressure. Sometimes with the same TDS, when you put, for instance, only sodium and chloride, it will be much different than different osmotic pressure with the same TDS, but with the distribution of the anions and cations. This is quite critical because in some tender specifications, they give you the TDS value and also the pressure limits. And if you put just the sodium and chloride, you cannot achieve that pressure. You are higher than that because you need to decrease sodium and chloride, but increase and distribute the other ions as well. There's a big engineering, as Gabi mentioned. There are crazy formulas behind, but this is the reason of the software program, which helps you to make it shorter and user-friendly, of course. So yeah, you just fill the form, how much like ppm of magnesium, sodium, potassium, and at the end anions and cations as well. What I can show here, let's say let's put 1000 of sodium, and then you have also potassium value of, I don't know, 10, and ammonium, let's say 300. And if you have only this cations, for example, you have to balance it, because always the water is balanced. But if you don't have the info about the anions, when you click calculate, it will add automatically to balance the cations. Usually, if it is wastewater, I would balance it with magnesium and sulfate. But if it is seawater or typical well water, I would balance it as sodium and chloride. But only with this information, to be honest, this won't be really a good quality of project, because as you see, it added only the chloride, because it's impossible to distribute. There's no any ratio, logical ratio between the ions. That's why the most critical one is chloride, so it add only chloride. So according to this analysis, you see osmotic pressure would be 41 psi, and also here on the left side, left corner, the most critical parameter, conductivity, will be calculated on based on the ions. When you click save, it asks you the name. Yes. Let's say Sarah. And when you click save, it moves this water analyze into design page, this one. So what we have done, we chose the water source, we put the water analyzers, and then we are almost ready for the design. But of course, what we need is the flow rate. What is the production, what is required, 100 ppm. You can choose permeate, as here we call it product, or feed water. Yes. And then you would need to put the needed recovery rate. For recovery rate, to have the highest value, highest idea, I always suggest to use first anti-scalant projection file software program, because according to water analyze, the maximum recovery rate that you can achieve would be like given by anti-scalant projection files. So even if I can add a lot of stages here and increase the recoveries, but it won't be a really healthy design, because according to water analyze, there's a highest value that you can achieve. Then otherwise, in the concentrate, it will be too much and it won't work on the field. Let's say you used it and you get, okay, this water can go up to, let's say, 55, 60, 75% recovery rate. Then you can start putting the recovery rate here. I will keep it now 50, because even it's too much, because it seems it's only one stage system. To increase the recovery rate in the projection, reverse osmosis projection program, you need to add stages. We chose seawater, so I would say for one stage seawater, maybe even 40% would be too high. But if you add from this button one more stage, the concentrate from the first stage would go into second pressure vessel. Then what it means physically is you are using more water to produce, because instead of wasting this concentrate, it will go again to another reverse osmosis system. Then maybe, I don't know now, maybe you can go up to 50%. Please remember, it's a seawater. In seawater with a high TDS, you cannot go up to, I don't know, 80, 90% recovery rates easily. Even maybe impossible. So, okay, now we are not trying to make a perfect design, but we want to show how it works, this projection, and we need to decide about the membrane type. In this list, you will see almost all the portfolio of our production. Because we chose seawater water source, we need to choose seawater membrane here. Now, in the name you can see, we have 3 different types of seawater: low rejection, medium rejection, and high rejection. Let's say easy. High rejection. For now, in this system, we will update it soon with the SWH, which is the highest rejection. But now in our program, it's SWM. 440, you see 440 and 400. Anybody knows what is 400 and 440? Okay. This 400 and 440 is it's a feet square. Unfortunately, it's a American unit is mostly used. The membrane area of the flat sheet area of the membrane, let's say. 400 is 400 feet square, 440 square feet. So the higher flat sheet you have, the higher flow you would have. But what is the advantage, disadvantage? You cannot use always 440, because when you have 440, they are the same, by the way. They can even one-to-one replaceable, because all the size dimensions is the same. But when you have more flat sheet, you need to have a smaller mill spacer between the flat sheet to make it more compact. But if the water is not very well pre-treated, then 440 membranes might not work properly. So if we are sure that pre-treatment is good, especially if there's a ultrafiltration, we would go with the 440 flat sheet, because with the same dimension you would have more water. The more flat sheet you have, the more water you would produce. Let's say a little bit. I don't want to use expensive word. I don't know how to say it. Yes, more flat. Huh? More valuable, yes. More water, let's say. Yes. So let's choose any of them, SWM 440. But we want to produce 50. Yeah, the 100 was feed water flow rate. So then we would like to produce 50 meter cube per hour. Then according to that value, we need to choose logical flux. Now with one vessel with 6 element and one vessel with 6 element, the flux seems 101, which is not logical. The seawater membranes system should be run around, I don't know, 12 or 13. So pressure vessels and 6. Why 6? To be honest, I don't know, but the standard seawater applications or brackish water application or any reverse osmosis membranes, 6 is if the flow rate is enough, 6 is most acceptable one. Sometimes in seawater applications, in one pressure vessel, 7 membranes are also used. But for, let's say, typical brackish water or typical systems have in one pressure vessel, 6 membrane next to each other. Maybe you remember the previous presentation. There was, I remember, pressure vessel and membranes next to each other. So why not 8 or 9? There are some technical reasons. So let's skip them. But if the flow rate is enough, 6 is or maximum 7 would be the best choice in the pressure vessels. But then we need to increase the pressure vessel number. So the feed water is coming from here, and then it will be distributed through the pressure vessels. So the more pressure vessels, the water per pressure vessel will be decreased. So the flux per membrane would be also decreased. How I start most of the time with the number of vessel, the decision, I would just start with 1 cubic meter per hour per membrane. So if it is 50, I would say here I would use 4 because, 8 because of like 48. But remember, this 50 meter cube per hour would be from both of them. So this won't be 50. Here, the flow rate would be 50. So just let's put 8 there, and let's see what will happen. In two-stage systems, also I don't know the reason, but usually the ratio between the stages would be 2 to 1. So if you have 10 pressure vessel in the first stage, in the second stage it will be 5. If you have 3 stages, why would we have 3 stages? If you want to increase the recovery, right? Because if we want to use this concentration water, we would add one more stage. Of course, the pressure will be higher, but we will have more water because we will not waste some part of this concentration as well. So if it is 3 stages, the standard in the market or in the systems, it will be most of the time 3, 2, 1. So let's say if it is, I'm trying to find the real logical number. Let's say 42 here. Then the second stage will be 21, and the third stage would be 7. Yeah, 3, 2, 1. Let's keep it 2 stages. Let's not be ambitious. So I would put here 4 pressure vessels. What will happen? Okay, without adding anything else, we can just see what would happen when we just run this project just like this. I click this calculate, and the program, without any additional feature of the system, the program will give you, just to show feed pressure, one of the most critical point, and permeate conductivity would be here. I don't remember how much was the feed conductivity. We can take a look. But as a result, just for a brief info, you would have with this system, or you would project with this system with the 23.6 bar, and you will get 52 microsiemens conductivity. Is it enough? I don't know. It will depend on your project. Sometimes 400 is enough. Sometimes even 700 would be enough. Or if you would like to work with a pharma application, let's say, they want as less as possible. Then what can we do? We can choose higher rejection, or let's say I would like to have less pressure because 52 is too much for me or too less for me. I would be glad with the higher conductivity. Then let's just to see the difference. Let's choose lower rejection membrane, which would be SWL. This L is basically low, M is medium. If SWL, both of them, and run the project, run the program. Then still, because the feed water quality was quite low, I think the conductivity, instead of 52, now we have 57 microsiemens. But it was feed pressure was 23, and now 20 bar. So the pressure depends on membrane type, right? The tightest membrane you use, the higher pressure you would have. So this is the logic. I don't. Is there anybody from pharma industry here? Still industry? Which industries? Okay. If you want better quality of water in some applications, we can add the pass. So basically, both of them are pass, but just to differentiate and to make it more complicated, they call it a stage here, and they call it pass here. When you say pass, the permeate from the first pass will be entered into second pass. Why are we doing it? To get better conductivity at the end. So that button was to add the second pass. Because this water has much less conductivity from the beginning, we don't have to use seawater, very tight membrane here, right? We can use a looser membrane, let's say, which is brackish water. Seawaters are membranes are tighter. Brackish water membranes are more looser. I don't know, standard 440, brackish water 440, let's say. You see here 34. Okay, I will not ask. 34. 34 means the thickness of the mill spacer between the flat sheet. So in the market you can find 28 or 34. Sometimes 31 also. But for instance, for landfill leachate applications, which I mentioned before, it has 48 mill spacer, which is even thicker. So mill spacer will help you to have not more water, but the easier water flow. Because it's the second pass, it's already treated in the first pass, I would choose 440, which has a thinner mill spacer to have more flat sheet. I would just choose this one. We can have the second stage on the second pass to get more water to increase the recovery. So how will I do that? I will add here the stage. It will automatically put the same membrane, but you can change the membrane type. Unfortunately, any kind of software program, reverse osmosis, it won't give you a suggestion of the membrane. You need to choose that because there are a lot of parameters and they all depend on what you need. As I just in the brief page mentioned, it depends on the conductivity that you are looking for at the end, or pressure. You would. That's why you need to choose the membrane type. Let's keep it like that. In the second pass, and regardless of the number of the stage in the second pass, this concentration has mathematically lower conductivity than the feed water. What does it mean? We can use all of this water and recirculate into the feed water to get better water quality just before the first pass. We are diluting the feed water with this water. So it will be a big waste if we put this concentration into discharge or something. How can I do that? There's a button here for recirculation. When I click it, you will see this page. And because this water is better than feed water, I can put the 100% all of the concentrate from the second pass into the first pass. I can choose here. Oh, before that, because I added the second pass, I need to add the permeate flow rate required from the second pass, which I forgot. So it's still 0. So let's say it was 50 entering, and then just to make it easy, let's say 20. And then it will mathematically calculate the recovery rate. Recovery rate is the permeate water divided by the feed water. Now we put, and then I have a concentration flow here, and I can put all the water into the first feed water. But let's run it like this to show. Yeah, it's good. I was looking for this. If you put let's say out of the limits, some parameters out of your limits, out of the system limits, because membrane can handle up to some features, some properties. Like you cannot, if the membrane can handle, I don't know, 12 LMH flux, you cannot try to push it to run with 20 LMH flux, for instance. Then it will give you the warnings of the design. How can I see that? What is the problem? In the brief, not, but here you will see. This is the pass one. In the pass one, there's no red color or any warning. But if you go here to the second pass, I put really wrong numbers here, as I see. This all red colors are the warnings. So these are the things that I need to change. It gives you also the hint. When I put it here, yeah, I put the really wrong numbers. You see the highest flow rate per membrane should be 18.2, but I try to push it to 50. To be honest, now I didn't notice. So what I should do, I should decrease the membrane, right? But now I remember what I did. I forgot to give how many vessels I should put, because now all this 50 meter cube per hour from the first pass are loaded into only 6 membranes. When the pressure vessel is 1 and it's a 6 membrane length, it means all of them are going to 6 membranes, which is really high. If you remember, I put here 20 to produce at the end. Then I mentioned I just roughly calculate 1 cubic meter per hour per membrane. So what I should do, I don't know, let's say to make it easier, 4 membrane, more than needed. I think 3 would be also enough. But what should I put here? 2, because again, in the stage ratios, the first stage and the second stage ratio should be, it's not really like a strict rule, but it works well. If there are 4 pressure vessels in the first stage, 2 pressure vessels would be needed. To make it's about the flux distribution, but to be honest, I also don't know the real mathematical or technical reasons for that. So when I calculate now, it didn't give any warning. Yeah, but I want to have warning. So I will put here 2 and 1. Let's see if it will be enough. Yeah, Let's see now what I did wrong or what I put out of the limits. It's usually flux or recovery. But before that, even with the warnings, if we design and if we push the system running like this, you see it was 57, I think, microsiemens. Now you have 0.18 microsiemens quality of water. These values are quite low. We use this water for semiconductor industry or pharma industry. Yeah, now I remember this too. Like we call it ultra pure water, not only pure water. Let's see again in the first pass, first stage to the second stage, there's no warning, but in the second pass, it says still. I remember it was 18 point something. Yes, I just moved the cursor mouse on the red color and do not click anything, and it gives you per element 18.2 meter cube per hour is exited. Yeah, because of the same reason, probably pressure per element of 1 bar is also exited here. You are pushing too much on the membrane to run. So the easiest solution, there might be some different solutions. The easiest solution would be increase the number of the membranes. I did the 4 and 2. I will run it now. And as I mentioned, I would like to have all this water into the first pass to dilute the feed water so that the load on the membrane would be easier. I did wrong. I added stage, but I need to click here to get the recycle. Like how much is the concentrate from the second pass is 30, so I can put here 30 cubic meter, which means, yeah, this water will go to the feed water to dilute it. And now I can also run. I'm pretty sure the pressure, feed pressure is now lower because feed pressure is totally based on the osmotic pressure of the feed water. It says now, I think it's exited because I recycled from the concentration from the second pass going to first pass. What I did, I increased the feed water flow rate. So there's a limit for the membrane to have a feed water. Then it increased. It's exited the 18.2 now. What I should do, either I can increase the membranes or decrease the recirculation. It all depends on you. Let's say we have the perfect design. Let's say there's no warning, hypothetically, and to see the full report, what kind of information I got from the projection. I click the report here. And I lost it. Yeah. This is the full report. What you get from this system if you run the reversal osmosis system just like this. In the first page, like the general information, the permeate flow rate and TDS, and for each stage, each pass, you will get the all ion values from the concentrate, from the permeate of each membranes. And the most important part is in total how many membranes you would need. In the first stage, you would need 48. In the second stage, 24. And at the end of the report, also these are the warnings, those red colors that we saw on the program. Yes. And combining with the antiscalant, also here I couldn't put, but also some here if there's a out of like LSI or calcium sulfate scaling warnings, they will be here. Then you need to talk to antiscalant producer to choose the correct antiscalant according to your water analysis and design. Lastly, I would like to show, this is the general idea of projection program. All really serious membrane producers have this kind of program because there's a big engineering behind it. A lot of field information gathered, and literally all the formulas and the parameters, they are all combined in the program, and this will help you for your system's predictions. Let's say your pump choice would be based on mostly, for instance, your projection program. UF design is much easier because it gives you almost all information already ready. You don't need to choose a lot of things here. Just quickly, I would like to show. When you choose here from start UF, this is the first page you will see, project name and etc. The feed water for UF, you don't need to put all those ions because ultrafiltration has nothing to do with the ions. Yeah, the ultrafiltration is mechanical filtration at the end, the particles. But what are the critical values is TOC, total organic carbon value, manganese value, because they are all changing the performance of the membranes, as well as pH and temperature, of course. If you remember antiscalant presentation, higher temperature you would have, higher in the reverse osmosis, higher salt passage you would have. Also for ultrafiltration, it's not salt passage, but it's getting looser again, and the performance would be lower, or let's say flux would be with the higher temperature, flux will be also higher because of the pores. So it's, or vice versa. With the cold water, it will be less passage, let's say particle passage. So after you put all these numbers, let's say TOC is 10, turbidity is also 5. Let's make it easy. And TSS is also, let's say, 10. When you click the system design, you would need, as usual, the flow rate, how much water you would like to produce. Let's say, again, 100 cubic meter per hour. As I mentioned, we have now 3 different membranes, ultrafiltration membranes, 3 different sizes. It's the same membrane with the different flat sheet square meter, 60, 80, and 107. If you have containerized systems, it's then you would need to use 60 or 80 because of the height of the membrane. But with the 107 square meter membranes, you cannot put it in the container. It should be outside of the container because of the height of the container. Let's choose 80, and then these values you don't need to do anything as a start, at least, because it will give you. Where is the running? Or SIP. I cannot. Yeah. The thing is, because of Zoom, there are a lot of buttons here. I cannot find calculate button. It will give you the similar report. Yeah, it's finished. It's finished. Almost finished. I'm just trying to. Unfortunately, I cannot click on the run button because there are a lot of Zoom windows. When you run the project just like that, you will get all the design. How many membranes you would need, how much CIP cleaning alkali, acidic, or if needed chloride cleaning chemicals you would need. You will have all those reports, and you can also change the in the system design. You can choose. If you think it can run with a higher LMH, you can increase the flux to decrease the number of the membranes and etc. And you will have the full report to get the idea, basic idea of the equipment selection, like pump or piping, diameter of the piping, PVC, etc. So this is the basics of the projection program. I hope you enjoyed. It's afternoon, I know, but I hope it was interesting for you. But if you have any questions, I would be glad. But I see only one participant has you have ultrafiltration membrane, yeah? Okay. And reverse osmosis membranes, you use reverse osmosis or you have reverse osmosis in your plant? Okay. And no pharmaceutical, as I remember. Okay. We will be in touch with Nihat, and thank you very much for invitation. And just as a basic, the more information you share with us for your systems, reverse osmosis, ultrafiltration, ISEP, other membranes, we can do our own design. We have a technical team in Italy in the production site, in Germany also in the production site. We are quite fast in returning, which will help you very well. Thank you. Thank you very much.
Zahvaljujem se gospodinu Arifu na izuzetno korisnom sadržajnom predavanju. Nastavu programa imat ćemo jednu pauzu, nekih 20 minuta, dok se uključi kolega Greg Johnson iz Nevade, pa eto, osvježite se malo ovih 20 minuta. Hvala vam na strpljenju.
Da li imaš tempo u svojoj ti meni ovdje otak ne ovdje kako se otak voda a se ne pozio smo pritisku ne znači tankice se ljudi i u space što znači
Hello, Greg. Do you hear us?
Yes, I can hear you.
Okay, I write you in the chat, but also I can ask you, do you want to share your presentation, or we can also share your presentation?
Either way, but yeah, I don't see a share button in my.
Okay, I will share for you. But you must say when you want when you want next slide. Just said next
Okay.
slide.
Okay,
That's it. Okay.
perfect.
We are starting about for 10 minutes
Okay.
with your
great, thank you.
presentation.
Yeah.
Welcome. You're welcome. Pucaj 226 883. To te šipka. Evo. Evo. 226.
Ja sam najputanija osoba. Svaka čast. Sad će Greg valjda da se uprije. Ti će vidjeti kako je. Ja se uključujem. To? Sve treba razgovarati, sad njih hoće da mi ja šere, sve smo mi dogovoriti. Samo ga najaviti, on piće. Okej. Eto. Ja. Četiri, pet, to ti kaže. Jesi tu pripravo. Ovo što ja, kada pašam, da. Posle vele, eto irim. Negacija. Plazma crkva. Ajde, ja. Šteta što nas je manje sada, sad dolazi po meni najinteresantniji dio. Evo, nakon pauze nastavljamo s posljednjim online uključenjem u Sjedinjene Američke Države. Veliko nam je zadovoljstvo najaviti predavanje Greg Johnsona, izvršnog direktora kompanije New Logic Research, jednog od pionira u razvoju naprednih membranskih rješenja. Tema njegovog izlaganja je tretman otpadnih voda i deponijskih procjednih voda, uštede operativnih troškova OPEX primjenom VSEP tehnologije. Implementacija potpunih Zero Liquid Discharge sistema, odnosno nulti ispust transformacija najtežeg otpada u čistu vodu i vrijedan resurs. Kroz ovo predavanje imat ćemo priliku čuti iskustva iz prakse i konkretne primjene VSEP tehnologije u tretmanu zahtjevnih voda uz poseban naglasak na optimizaciju procesa, povećanje efikasnosti i značajno smanjenje operativnih troškova, što je danas jedan od ključnih izazova u upravljanju vodnim resursima. Izvolite, gospodine Greg.
Hello, am I going to be starting?
Yes, now I will share your presentation. You can start.
Okay, great. Yeah, thanks to everybody. My name is Greg Johnson. I'm the CEO of New Logic Research. I'm also one of the founders of the company. So yeah, we can go ahead and go to the next screen. So I'm going to be giving a presentation about our vibratory membrane system. I watched a little bit of the previous presentation about spiral membrane systems. And spiral membranes is a great technology, and it has many good uses. A spiral membrane also has some limitations, and that's where our membrane system would come in. We don't have those same limitations, so there would be a place to use both types of technologies. So this particular presentation, I'm going to be talking about mostly about treating power plant wastewater, the flue gas scrubber wastewater, which is a big deal in the United States. The EPA here is formulating regulations for discharge of this water, and we have a lot of experience with that. So even though we can do many applications, I'll be focusing on that. But to give you a background about the company, This is not new technology. This is proven technology that's been deployed around the world. We have hundreds of installations all over the world in many countries, you know, in South Africa, South America, Australia, Korea, of course, here in North America, and we have many projects in Europe as well. We're located in Nevada, California, and we have our main manufacturing facility here in Nevada. We do business internationally, and a lot of times we will do that through distributors and representatives like Kiwicon, companies that assist us and are locally placed so that they can be available for meetings or technical discussions and things like that. So go ahead and go to the next slide. And just to give you the background on the company, how we started, one of my partners is a PhD chemical engineer, a very smart guy, and he used to work for a company called Dorr Oliver, which is a filtration company. They made laboratory filtration devices, and so he became familiar with membranes and the limitations of membranes. And he had the idea that if you vibrate the membrane or resonate the membrane, it creates a lot of shear at the membrane surface. And that shear is very important because it disrupts something called concentration polarization. So basically, when you're filtering something, the liquid passes through the membrane, but all of the solids are rejected and left behind. So they can accumulate, these solids can accumulate on the feed side of the membrane, and they can accumulate and get so concentrated near the membrane that it can cause all kinds of problems. One thing that'll happen is if you exceed the solubility limit of something and you have a super concentrated amount of solids near the membrane, you can get scaling and fouling of the membrane. So his idea was to create shear that would disrupt that ability to have a concentration gradient, and it would keep all of the dissolved solids homogeneous in the bulk flow of the liquid. So the very first device that we created was actually for a pharmaceutical company. That's how we began. The very first machine we made, a pharmaceutical company wanted to create a blood separation device that a doctor could use in his office, a very small tabletop device where he could use a membrane, he could filter a blood sample and remove the red blood cells and the larger materials and have a plasma go through that you could do testing in the doctor's office. So that's how it all began. The very first VSEP you can see here in the picture, very small device. It worked and didn't have any fouling or scaling issues. So this is how it all started. And of course, the equipment got bigger from there. So we can go ahead and go to the next slide. And so this is our new facility in Nevada. Like I said, we used to be located actually in the San Francisco Bay Area, but we moved up here to Nevada. We're just on the other side of the mountain from Lake Tahoe, if you know where that is. We have a much larger facility now in Nevada. We do all of our manufacturing, engineering, sales, and other activities at this location. Our company has been growing since 1987, and we actually have purchased purchased an empty lot next door to this facility, and we're going to be putting up a second building next door, probably next year. So that's just so you can visualize what our company looks like and where we are. There we go. we've installed hundreds of systems worldwide. Like I said, this is proven technology. It's not brand new. It's not experimental. It's been used hundreds of times and by many multinational companies, as you can see here. We're in all kinds of different industries. And usually the applications that we get are difficult applications. And so we're in oil and gas, food and beverage, pulp and paper, power plants, landfills, industrial manufacturing, you name it. So we have a very diverse clientele. After now almost 40 years of dealing with difficult separations, we've done just about everything. All kinds of wastewater. We have experience with that. And we've learned a lot because of all this experience in doing many of these applications over and over again. So we have a very good depth of engineering knowledge and history with the company. Go ahead. So just to give you a background on the technology itself, you saw that it started out with a very small device, but now the membrane systems are very large. So one of our filter elements, we call them a filter pack, contains about 130 square meters of membrane area. So it's very large. And the way that we do that is a little bit different than a spiral membrane. In a spiral membrane, you have you wrap the membrane around a center core, and you use a plastic netting spacer to separate the membranes. So it's a very compact element. You can put a lot of membrane in a very small area. Our membrane configuration is a little bit different. It sometimes is referred to as a plate and frame type of membrane. So what we do are we take circular discs of membranes. We start with a stainless steel support layer, and then we apply a drainage cloth on top of that to provide a space under the membrane, and then we put a membrane on top of that. And these circular discs, they're about a half a meter in width. And the reason that we decided on that diameter is that we can get 2 pieces of membrane out of a 1 meter wide roll of membrane. So we buy the membrane in a flat sheet roll, and then we cut it into circular discs like this and apply it to a stainless steel disc. And then these discs are stacked up on top of each other. There'll be about 500 of these trays. We call them a membrane tray. And they're stacked up vertically into the filter pack. The height of that filter pack is a little more than 2 meters in height. And what happens is the wastewater or the feed liquid goes into the top of the filter, and then it passes through. We have 2 holes in each of the discs, it's sealed with a grommet. So the wastewater will pass down through the holes, and then periodically we block the pathway so that the liquid has to travel from one side to the other. And then it'll go down further. We block another hole. So basically the wastewater is cascading down through the filter. And so the wastewater starts at the top, and as the pressure is applied and the liquid is traveling through the membrane, the permeate is passing through the membrane and then is pulled out through the center and comes out the top. And then as you get to the bottom of the filter, the material, of course, is more concentrated because you have removed permeate. So you have a concentration gradient inside the filter. So that's the filter construction and how it works. It's different than a spiral membrane because they're stacked on top of each other instead of spirally wound. The other difference is there's a fairly wide space between the membrane sheets. And so with a spiral membrane, you know, it's a pretty tight space in there with the netting, and there can be limitations for suspended solids. Often, if you're using an RO membrane, you would need to use a UF membrane or some other pretreatment step to remove suspended solids to have a low SDI. With our system, we don't have any limitations on suspended solids because of the wide spacing. So the suspended solids will just pass freely through the filter. It'll cascade down through and become concentrated along with the dissolved solids. So this is the filter design configuration, just so you can visualize what that is. And so you can go to the next slide. And so here's at a very close level to the membrane is an animation showing the difference. With the spiral membrane, basically they use cross flow, laminar cross flow, as a way of creating shear to keep the membrane clean. So cross flow membrane is better than dead end filtration. But the laminar cross flow has limitations because the drag from the membrane reduces the amount of shear the closer you get to the membrane. And with our system, we're actually moving that membrane back and forth 50 times per second. And this creates very high shear at the membrane surface that prevents materials from attaching to the membrane and also disrupts the concentration polarization. The membrane is moving back and forth 50 times per second, and it's traveling about 1.3 centimeters peak to peak. And it's so with 50 times per second reversing direction, every time it reverses direction, it's pulling an incredible amount of G forces. So it would be very difficult for something to want to attach to the membrane and hold on to the membrane because of this incredible force that is preventing it from attaching to the membrane. This is the reason that we don't have limits for suspended solids, and this is what disrupts the concentration polarization and prevents scaling of the membrane, because you have a homogeneous feed material, and we can have precipitation in the membrane. And what happens is the precipitation just occurs at good nucleation sites, which are suspended solids out in the bulk flow. So we don't stop when something might precipitate in our membrane system. Most of the applications that we do, the feed material is already supersaturated. And so precipitation is something that happens normally in our system. We can actually precipitate solids while filtration is happening. So the next slide will show you how we do this, how we resonate the membrane. So you can go to there we go. So what we do is there we go, that's fine. We have a mechanical steel structure below the filter. And the way that we do this is there's a 20 horsepower motor that is spinning an eccentric weight. You can see the yellow eccentric weight, and that induces a wobble effect. And there's a steel mass on the bottom, and then the filter mounted on top of that round plate. And what happens is when this structure reaches a very specific frequency, the entire structure begins to resonate. So it's not a forced mechanical vibration. It's actually a resonance that's occurring. Resonance is something, vibration and resonance is something that you can get. A lot of mechanical engineers are taught that resonance or vibration is bad, and you need to design something that doesn't vibrate. But in our case, vibration is exactly what we want. And so the entire design of the structure is built that way to allow this vibration to occur. The aspect ratio, the dimensions, the weight, everything about the structure is very specifically designed so that when you're operating a motor that's spinning a bearing at about 50 hertz, the entire structure begins to resonate. So that's the basics of the VSEP technology. It's a membrane system. Spiral membranes are very good, and they have many good uses, and you should use a spiral membrane if you can, because they will be less expensive than our system. Our system is going to be more expensive than a spiral because of the steel structure and the robust design that needs to be built in order to accommodate this very rapid movement. So our system is not an alternative to a spiral. It's a complementary technology that can be used either after a spiral to take the reject from a spiral membrane, or to be used in applications where a spiral membrane would have a lot of difficulty. Our membrane system is more expensive than a spiral, but it's less expensive than evaporation or hauling or other ZLD options that you might have. Most of the projects that we do are ZLD, and most of the projects that we do have very high concentrations of hardness and organics and suspended solids and things like that. So the best fit of our equipment is between a spiral membrane system and an evaporator technology, because our system is much less expensive than evaporating the water. So we can go to the next slide. This just gives you a visual picture of the amount of shear at the membrane surface. So you see the two layers of membranes. The illustration on the top shows a conventional spiral membrane system. This uses laminar flow or liquid velocity pumping power to push liquid through the space between the membranes so that you can create shear to try to keep the membrane clean. And as I said, because of the drag from the membrane, the closer you get to the membrane, the less shear you have, the less relative velocity that you have. So because of that, you can get an accumulation of solids, a concentration gradient right near the membrane surface. With our system, the illustration on the bottom, it shows the very rapid movement of the membrane has the highest shear near the membrane and very gentle flow out in the middle. So we're not using a lot of pump velocity to push the liquid through the filter. The liquid is actually traveling very mildly through the filter while the membrane is doing all the work and the membrane is moving back and forth. Next slide. So this is what, just to give you a picture of what the system looks like. On the left, you see a side view of one of our systems. The yellow circular tubes are the membrane filter packs. This image shows a 4-module VSEP system. Each one of those VSEP modules has 130 square meters. Just to give you a rough idea, it depends on the application, but if we're using an RO membrane, each one of those modules will do something like 4 or 5 cubic meters per hour throughput rate. The nice thing about the VSEP system is that it's modular, and you can put any number of VSEP modules in parallel for any flow rate that you have. We design the systems to be modular like this The VSEP filter stands independently by itself, and then it's connected to a feed, what we call a feed pump skid, which on the right, you can see towards the bottom in the middle, there's a skid that has the pumps, valves, instrumentation, controls, everything is mounted there. And there's some interconnecting piping that will distribute out to each of the VSEP modules and connect each of them. So the system is, of course, automated, and it runs all of these modules in parallel. The other nice feature about our membrane system is that the cleaning, periodically, of course, membranes need to be cleaned, even our membrane. And the cleaning can be done on one module at a time. So the system is never down completely if you have to do a cleaning. You just simply take one module offline through the valves and the headers that we have on our skid. And to the right there, you can see that small yellow tank. That's a cleaning tank. That little skid there will operate one VSEP machine and perform a cleaning. After that VSEP machine is cleaned, it will put it back online, and then the system would automatically go to the next module and do a cleaning. So there's a couple of nice features. The VSEP is modular. You can easily expand it by adding more modules if you need to. And it's also nice that it's because it's vertical, the footprint is fairly small, and you can clean the filters individually. So that gives you a picture of what a VSEP system would look like. And we can go to the next slide. So then talking specifically about power plants, of course, we have hundreds of installations. And I would say in Europe, probably our biggest application is treating biogas effluent from anaerobic digesters. As you know, renewable energy is a big thing. And so biogas is encouraged in Europe. It also helps with a way of disposing of manure, food waste, other organic materials that would be land applied and perhaps land applied too much. So it's getting value out of the organic material. The digester effluent can have very high suspended solids, very high organic loading. It can have struvite and other types of scale forming materials in it. And our system is able to filter that directly, take the effluent from the digester, filter that with an RO membrane with only 120 mesh screening and no other pretreatment, and then produce drinking water quality from that effluent. So that gives you an idea about the capabilities of our membrane system. So biogas is probably number one in Europe, but I'm going to be talking about power plants here. And power plant is another industry where we've been very successful for many years. There are several applications in power plants. Every power plant will use a cooling tower, and there's going to be blow down from cooling towers, and it's the reason they're blowing it down is they don't want to scale their heat exchangers. And so this blow down is going to be super saturated. So that's a perfect application for us. Another thing that happens at power plants is they are required to collect all of the storm water, any rainwater or any other water that hits their property. It then belongs to them and has to be treated. So that would be another application. But specifically for this presentation, the subject is the treatment of the flue gas scrubber water. So it used to be power plants didn't have scrubbers on their flue gas. And of course, that would put a lot of sulfur into the atmosphere, and that would cause acid rain as the sulfur would convert into sulfuric acid, and it led to a lot of problems, including increasing the acidity of rivers and things like that. So most modern power plants have now installed flue gas scrubbers. And so the way that they do that is you use limestone to liquefy, you add lime and water, and you spray a mist to the top of your flue gas. And as the mist of water and lime is coming down through the flue, it collects all of the sulfur and the pollutants and arsenic and mercury and things like that. And so you're basically, instead of putting those things into the atmosphere, now you're putting them into water. And so now you have a wastewater problem instead of an air emission problem. So it's simply collecting the pollutants, but then these things need to be treated. And because you're adding lime, of course, this wastewater is very concentrated in calcium and sulfate. And so you have a lot of gypsum in this type of wastewater. It's the solubility of calcium sulfate is fairly low. It's about 2,000. And in most cases, the FGD wastewater is going to be at that level or higher. So this is another good application for us because it's near its solubility limit. You may be able to use spirals for this, but because of that solubility limit, it would require softening and a lot of other pretreatment. With our system, the only thing we need to do is have pre-screening. And after pre-screening to remove sand and large particles, we can directly filter FGD wastewater with an RO membrane. So we can go to the next slide. And FGD wastewater is a very complex, and it can vary a lot. And so it makes it difficult. If you're designing a spiral membrane system, you input all of the values of your dissolved solids and things like that, and you assume that they're not going to change. And the input values will tell you what recovery rates you can get, what flux rates you can get, whether you need anti-scalant, all of the other features of a system design. But the risk and the difficulty is that the FGD water may not always be the same. The contaminants that the scrubber is taking out will depend on what's in the coal that's burned. It will also depend on what's in the limestone that's used. And both of those can vary depending on where they're coming from. And so it doesn't, with the spiral membrane, the risk is if your minerals that can cause scaling, if the concentration of those minerals changes by 50 milligrams per liter, that can have a huge impact and could risk problems with your spiral. Because our VSEP membrane doesn't have solubility limits, because we disrupt concentration polarization, a little change like 50 or 100 milligrams per liter in sulfate concentration isn't going to affect anything in our system. So we have a lot of experience with FGD water. We know that typically the chlorides are very high, and typically this will require special alloys for construction so you don't get corrosion. The scrubber is also a forced oxidation device, and basically you're converting sulfur to sulfate, and so the wastewater can also have a high ORP value and have an oxidative characteristics. So you need to think about adding reducing agents so that you don't damage the membrane. So it's a very complex wastewater. It can change over time, and there are a lot of things that you need to consider in the design when you're treating this kind of wastewater. So we can go to the next slide. And so the VSEP system, we have a lot of experience with this wastewater. With our system, we don't have the same limits as a spiral membrane. We don't have solubility limits. We don't have limits on oil, organics. We don't have limits for lots of things that would determine the endpoint for a spiral membrane. The one limit that we do have is the law of nature, which is osmotic pressure. So as you increase the concentration of dissolved solids, you need higher and higher pressure to get the water to go through the membrane. That's just a law of nature. The rule is that you'll need to have an even concentration. You can't have one pure water section sitting next to one water that has a lot of salt in it. They'll want to mix, and you get that with a membrane. You can have clean water on one side and salty water on the other side. So the law of nature says that clean water will want to mix with the salt water. The reason that they call it reverse osmosis is because you're trying to get the water to go in the reverse direction that it wants to go by nature. And so the way that you do that is with pressure. You can push the water and try to overcome that law of nature using pressure. That's called osmotic pressure. So that is a limit for us that even the vibration can't solve. And so we have limits when it comes to the endpoint. With our standard system design, we can get up to about 5% TDS. And with our higher pressure design, we can get up to about 10% TDS. But that's really the only limit for our system is the TDS concentration, and FGD water can have pretty high TDS. The other limit is we just can't have large sand particles and things like that going in. And we go to the next slide. To give you a history, I think that in the United States, there has been a lot of focus on coal. And of course, there is a movement towards renewable energy. And, it seems to me that having a diverse energy mix of lots of different fuels and lots of different methods of producing energy is a wise solution to have. Renewable energy has its place, and nuclear has its place. Hydroelectric power has its place. Coal also has a place. The nice thing about coal is that you have your fuel is stored at the power plant. In winter, when the sun is not shining or it's not windy, renewable energy is you can't increase the energy that you get from that, and it may be reduced because of the weather. And also in very cold weather, natural gas can be a problem because your valves can freeze and the pressure in your pipeline can be reduced. And so the natural gas is not stored at the power plant. If the pressure in the pipeline gets too low, a power plant would have to shut down. And so coal is nice because you have the fuel right there at the power plant. And in wintertime, that can be a big deal. And so, there is a movement in the United States, there is a movement to get away from coal. But that's, yet to be decided. There's people on both sides that believe that we need a wide energy mix. So anyways, the EPA here is our environmental organization. They're creating rules for coal-fired power plants because the FGD wastewater is unique to coal-fired power plants. Coal has a lot of sulfur in it, and natural gas doesn't. And so you don't have the same kind of wastewater in a natural gas power plant that you do with a coal power plant. So the EPA is working on these regulations. They have been for a long time. They're developing the rules, and at some point they will be implemented. So there's an industry organization called EPRI, which is Electric Power Research Institute. So it's an industry organization funded by power plants. They do industry research for power plants for the benefit of the industry. So we've done many collaboration research projects with EPRI that was funded by EPRI, including we've done a couple of nuclear power plant wastewater projects with EPRI using our VSEP membrane technology to filter radioactive wastewater. But more than 10 years ago, we did a large FGD wastewater demonstration project at the largest coal-fired power plant in the United States. That demonstration project ran for a couple of years, and the results were good. EPRI wrote a report about how the VSEP was able to treat the FGD wastewater and meet the proposed rules from the EPA. So we have a good experience for a long time with this wastewater in collaboration with the industry organization here in the United States. As a result of that work that we did, the EPA, of course, is always looking for technological solutions. They were aware of that demonstration work, and as a result of that, the EPA has named our membrane system as a best available technology for FGD water treatment. So we can go to the next slide. This is a basic block diagram of a VSEP system for treating FGD water. So in the United States, the proposed rules are going to be very strict for the final treated water. Even very low, like mercury, has to be below 15 parts per trillion. And it could be 10,000 parts per trillion starting. So we can't, membranes have a very high rejection and can produce very clean water. But to make, a 99.9% reduction, you need more than one pass with an RO membrane to get to the very low levels. So this shows a typical VSEP system. There's a primary stage of VSEP with RO that takes the screened raw effluent, filters that, and the permeate from the VSEP, the RO permeate. Now your dissolved solids and things have been reduced by 90 to 95%. That clean permeate goes to a conventional spiral RO membrane system. Now, because that water is cleaner, it doesn't pose any risk to the spiral. The spiral performs the polishing and gets the contaminant loading down to very low levels. And in order to reduce the volume of the concentrate even more, we'll use a second stage VSEP concentrators system, and that may be our high pressure design that can get us up to about 10% total dissolved solids. And then for the complete ZLD solution, the final concentrate from the VSEP would go to thermal evaporation. So this flow sheet here would be better than just evaporating all of the water. Because the VSEP system is going to be out about if you figure CapEx and OpEx, total cost of ownership, the VSEP is going to be about 10% of the cost of evaporating. So the best thing to do is dewater as much as you can prior to evaporation, and then use the evaporator at the end for a total ZLD process. In this way, you get extremely clean water that could meet any kind of discharge requirement. You also get clean water that can be reused in the power plant for cooling tower makeup or boiler feed or any other process need you might have. But a lot of times, you know, some kind of discharge would be needed because in a power plant, you'll have a water balance problem because you're collecting stormwater as well. And you have leachate from your fly ash. And so that water that you're collecting is a positive balance. And so some amount of water will need to be purged from the power plant. But that clean water is there for makeup water. And it's also an added benefit. So we can go to the next slide. And I'm not going to go through each of these things here, but this is a mass balance for that previous slide you saw. I think that the organizers of this seminar will be able to give you a copy of this presentation so you could study this in more detail. But basically, this is a mass balance for the first stage. The first column, it shows you the blended feed is the FGD wastewater. The second column is the VSEP permeate. So just as an example here, you can see the sulfate is about 1,200 milligrams per liter in the wastewater. After the VSEP, it's 4. And then that second column water would go to spiral for polishing. So you can go to the next slide, which is the mass balance for the stage 2. I won't go through the details here, but this is available if you want to study each individual dissolved solid and see how we do. And the next slide is finally the spiral RO polishing. And you can see they're extremely low levels in just about everything after 2 passes with RO. You could even use a 3rd pass with RO if you need to, depending on what the feed solids are. We can, of course, simulate all of this with the input values, just like our spiral friends with the presentation earlier. We have a software program where we can input the values and then produce a mass balance like this. It also helps us to determine how many stages are needed, what the osmotic pressure will be, and all of those kind of things. So that's the mass balance. The takeaway from all of this is our membrane system is, yes, we use membranes. We use the same exact membranes that other spiral membranes company use, but we deploy the membrane in a different way. We don't wind the membrane around a center core with a plastic netting in between with very tight spaces. We use a plate and frame type design with a wide space between the membranes. We vibrate the membrane, and that disrupts concentration polarization. Because of that design, we don't have limits for solubility. We don't have limits for suspended solids. We can take 5% oil. All of those things won't affect our membrane. Our membrane is more expensive than a spiral membrane because it's built a lot more robustly, and it's more expensive to build. And it's not an alternative to a spiral membrane. It's a complementary technology. Many of the projects that we've done, we take the concentrate from another spiral membrane system and volume reduce that further. And because we're not limited by solubility, And because we actually precipitate solids during filtration, our membrane system is actually an alternative to a crystallizer. So it's actually a membrane crystallizer where we're precipitating solids, even gypsum, while filtration is occurring. So the way to think of our membrane system is not really a membrane system, but think of it as an alternative to a crystallizer or an evaporator, because the economics, the cost of our system will be less than the cost of thermal evaporation or crystallizing. So we can go to the next slide. The other thing about our system is simplicity. You know, spiral membranes are great. They have many good uses. And we actually build spiral membrane systems, and we can supply those. We use them when they're appropriate. But sometimes spiral membrane systems can require significant pretreatment, perhaps softening, perhaps ultrafiltration, you know, other things to minimize the risk to the spiral membrane system. With our system, the chemical addition is usually not required. And we can usually just take raw wastewater with wire mesh screening and filter that directly with an RO membrane. The exception for FGD water is because it's an oxidative environment. High oxidation potential can damage membranes. So we just sometimes for FGD water will need to add reducing agents to get the ORP down to a safe level so it doesn't damage the membranes. Because of the vibration, fouling is vastly reduced, but it's not 100% eliminated. So we do clean our membranes periodically, just like any other membrane system. And so really the only chemical additional requirements would be possibly reducing agent if the ORP is too high, and then periodic chemical cleaning. Other than that, we don't require any softening. Usually we don't require any anti-scaling or pH adjustment. So it's a very simple system to use. I'll go to the next slide. I was saying we have a pretty good experience in power plants. We've done several cooling tower blowdown projects at full scale. Many different kinds of applications. We know the unique characteristics of a power plant. A lot of them don't have a lot of people, operators running around the plant. Everything is automated. And so we understand the need for automation, the need for low maintenance, and our systems work well in an industrial facility, a power plant, where you don't want to have a lot of people running around and you don't have a lot of manpower available. So we have good experience as far as that goes. And the next slide. And then the way that we, our systems are usually large. We're handling big volumes of flow rates, and wastewaters can vary. Even FGD wastewater will vary quite a bit. You can have high chlorides or low chlorides. You can have high TDS and low TDS. So we can simulate everything, and we can produce a mass balance and estimate a project based on historical data. But we do recommend that pilot testing is done to confirm everything. So we have pilot test equipment that can be rented. We can ship the pilot equipment, either manual systems or automated pilot systems. And we can send the equipment to your facility. And then we would send a technician out there to get everything up and running. We can run that for a period of time, collect analytic data, collect flow rate data, and use that to confirm the system design before we go full scale. And when it comes to the pilot testing equipment, we have smaller equipment like this one shown in the picture. but we also can rent full-scale systems. So there's a wide range of pilot testing options. And this gives the end user good confidence level because they can see the system in operation at their facility, running on their wastewater. And it gives them a lot of people aren't familiar with our membrane. They might know about membranes, but not ours. So it also gives them a chance to see how the vibration works and see it firsthand, and that can be very helpful. Okay, next. And that's the end. I don't know if we're connected so that I can answer questions, but I'd be happy to do that if that's available.
Thank you, Mr. Greg.
Thank you. Yeah, thank you all for
very much.
the opportunity. I appreciate it very much. Thank you.
Okay, bye. Thank you very much and see you soon.
Okay, bye-bye.
Evo, došli smo do kraja. Bilo je malo možda i naporno držati koncentraciju svo vrijeme, ali svaka vam čast. Sad ću ja jednu kratku završnu riječ, pa da završimo današnju sesiju. Poštovane dame i gospodo, drage kolege i kolegice, polako dolazimo do kraja današnje Balkanske radionice membranskih tehnologija. Želim vam se svima iskreno zahvaliti što ste bili dio ovoga događaja. Današnji susreti, diskusije i razmjene iskustva još jednom su pokazali koliko je ova oblast važna, ne samo sa tehničkog aspekta, nego i za širu društvenu zajednicu. Membranske tehnologije danas nisu samo napredna inženjerska rješenja, već ključni alat u očuvanju vodnih resursa i zaštite okoliša. Meni lično je bilo veliko zadovoljstvo biti dio ovoga skupa i vidjeti koliko znanja, iskustava i dobre energije postoji među ljudima koji se bave ovom oblašću. Danas smo imali priliku čuti zaista različita iskustva od naučnih pristupa do konkretnih inženjerskih rješenja koja se već primjenjuju u praksi. Posebno mi je drago što je u svemu ovome prepoznata uloga industrije i kompanija koje rade na terenu. U tom smislu bi istakao i rad kompanije Igrakom d.o. Sarajevo, koja kroz svoje projekte u oblasti pročišćavanja voda i membranskih sistema pokušava da poveže ono što učimo i razvijamo na fakultetima s onim što se dešava u realnim postrojenjima. Mislim da je upravo to most koji nam svima treba. Ono što me posebno raduje jeste činjenica da ova radionica nije bila samo niz prezentacija, nego i prostor za razgovor, za razmjenu ideje, iskustva i potencijalnih zajedničkih projekata. Vjerujem da je upravo to njen najveći rezultat. Posebno je zadovoljstvo što smo danas okupili stručnjake iz različitih zemalja i institucija. Upravo ta raznolikost znanja i iskustava daje dodatnu vrijednost ovoj radionici i predstavlja temelj za buduću saradnju na regionalnom nivou. Vjerujem da smo kroz današnje prezentacije i razgovore otvorili nova pitanja, ali ponudili konkretna rješenja i ideje koje će svako od nas moći primijeniti u svom radu. Želio bih se zahvaliti svim predavačima na izuzetno kvalitetnim izlaganjima, kao i svim učesnicima na aktivnom učešću i konstruktivnim diskusijama. Također posebna zahvalnost ide domaćinima sa Mašinskog fakulteta u Sarajevu, koji su omogućili da se ova radionica održi na visokom nivou. Na kraju, nadam se da je ovo tek početak jačanja regionalnih partnerstava u oblasti membranskih tehnologija i pročišćavanja voda. Pred nama su veliki izazovi, ali velike prilike. Vjerujem da ih možemo uspješno savladati upravo kroz saradnju. Još jednom vam hvala na dolasku, želim vam sretan put kući i radujem se svakoj budućoj prilici da ponovo surađujemo, možda već vrlo brzo na nekim novim konkretnim projektima. Ovim putem proglašavam Balkansku radionicu membranskih tehnologija zatvorenom. Hvala vam.